All right. So the first problem that you might encounter with cylinders, the cylinders are annoying. So I'm just warning you, they can be pretty annoying. You have a very long solid cylinder of radius capital R. When it says very long, it's keyword for infinite. Okay, you can assume it's infinite in the extent of Z here. And it says also, to make things more annoying, that you have a charge density that varies with R, because who doesn't want that, right? So we have this kind of dependency. You can see the dependency here. It's an R dependency. Okay, and then we want to calculate the electric field everywhere, and then I'll show you how to do the potential as well. So let's roll immediately, okay? You see the charge density here, dependent on R. To me, again, I can sit here and talk to you 10 minutes about this, why that is, with different points like I did for the plane, for example. But I will skip that for now. You're not taking Phys 242. You don't have to justify why you're doing this. I'm just looking at the R. Immediately, I know that the function here of the electric field, okay, what is it going to look like? It's going to be dependent on R, okay, just from looking at the charge density here. And then I go and look at the diagram, and I'm thinking to myself, okay, this is a solid cylinder. This is like a line, basically a thick line, you know? And how did the situation for our line look like back when we did it in the beginning? I recall what I've seen from the past. And I remember that a line, like for example, something like this, had an electric field that's like pricking out like this, like thorns all around it. And that electric field was going in the cylindrical R direction. So if it's a thick cylinder, it has the same kind of symmetry as the thin line. And I expect then, okay, I expect the full electric field to be dependent on R, but also pointing in the cylindrical R. These are cylindrical Rs. In Math 119, we call them rows, if you remember. Okay, having said that, I need a surface now, again, where the electric field on it, right? Or at least at some part of it. Remember, it doesn't have to be the whole thing that experiences the same electric field strength. It can be just a part of it, just like we did with a Gaussian pillbox yesterday. It can just be a part. We didn't do yesterday, actually, it was a while ago. But if you recall, when I put the box here, okay, I did it here. It was just 1 and 2 side here, side 1 and 2, that experienced uniform electric field. The others didn't experience anything. So we don't have to do it for all sides, you know? We just need a shape that experiences uniform field from some sides, okay? And, you know, you look over here, I've already spoiled what that surface is gonna look like. Obviously, it's gonna be a cylinder, all right? So I'm gonna make it, again, I have 2 regions for this charge density, okay? One is inside and one is outside. So let me explain what I mean by that. Really, rho is like this. It's a piecewise function, right? So it has this dependency when you're on the inside, but it has nothing when you are on the outside here. So I expect, again, from this, I expect 2 electric field regions. And you can see how they're going to split up. Each one of them here is going to give you 1 electric field that's unique. All right, and we talked about why we expect the electric field to be, again, a function of R and directed in the R. So let's keep moving then. We got to do then Gauss's law for these 2 regions, okay? And so I start with the inside. Let's do the inside. So again, I'll write down my Gaussian integral, okay? E dot dA and all the good stuff, okay, is equal to Q enclosed over epsilon naught. All right, and so you go, okay, how much charge have I enclosed? You know, what does the left-hand side look like? That's the stuff that we gotta answer. Right now, again, we said the electric field of the cylinder here is always going to be penetrating our Gaussian surface, as you can see, the normals on the sides always going to be parallel to that electric field, okay? But as you can see, the top and bottom of our Gaussian surface are not going to receive any electric field through, which is okay. We said we only need one of these sides to receive electric field. We don't need all of the entire closed shape to do that. In this integral, remember how we used to break it into two parts, or multiple parts rather. Here in this case, I can break it into the side, I guess, of the cylinder, and then I can break it into the caps. But the caps, like we said, no electric field crosses them. Therefore, this integral is actually 0. And you only have to do the side. Now on the side, we have the beautiful simplifications with the normals in the electric field. And don't forget that your Gaussian surface has a constant radius r for its side portion. Everybody that's sitting on the side has a constant value of r, ensuring that the electric field is constant across the entire side of the cylinder, which means the electric field goes outside the integral as usual. And then you have to do over here, you have to calculate the area of the side of the Gaussian cylinder. Let me assign that to Olivia right now. What is the area of the side of the cylinder? If I make it again, Olivia, here, I'll give it some random length here, L. What do you know about this?
So it's the area of a circle times L. So it would be pi r squared L.
You're thinking volume. That would be volume.
Just for the surface area?
Right. For the surface area, we have a rectangle. If you snip the cylinder, you have a rectangle. And this side is something, this side is something.
Oh, yeah. Okay, so you have L, and then you have 2 pi r.
Mm-hmm. Perfect. So 2 pi RL. Beautiful. So if I, again, now open this up, you see what I get? I got E 2 pi RL. And now we're waiting for the other side, right? So on the other side, we have a volume density here, okay? And that means that you can get right now the charge enclosed. Usually you do, if I ask Kelly, Kelly would tell me do rho times dV here, or rho times V. You got to integrate it this time though, because it's a variable charge density. It varies. It's not uniform. I can't just multiply. You can't pull it outside the integral right now. That's the problem, right? That's what sucks about this. But that's okay. That's why I picked this problem, to show you how to deal with this. So this row needs to go in as is, dry right now. We're going to have here a triple integral. Rho is, well, rho naught times r. And I doubt that anybody remembers the volume element in cylindricals, but I'll show it to you nonetheless. Okay, you got here the area element right now, this dA, where this is going to be r d phi, that's going to be dz, and you got extended backwards toward the origin here. I hope I'm doing a decent drawing, and that is going to be your dr right now. This hold on, let me do it properly. It's going to be your dr. So all together, you see what we're going to get: r dr d phi dz, and we have this in our geometry notes. At least I do over here. There. So if you ever forget, I can give you this file. Here is the one that we're looking for, the volume element on the side there of the cylinder, right? But no matter how you derive the volume element, if you did it from the top here, we'll give you the same answer. Volume elements are the same. You know what I mean? Area elements are not, of course. This area element is not the same as this. But yeah, you can see here what we get. So r dr d phi dz. Going back now to your problem, we literally plug that guy in here. Let's go and do that. We got r dr d phi. You haven't worked with this one a lot, so whatever, you get to see it now. And I want Grace here to try and fill in the bounds of this triple integral, it's not math 119 difficulty, don't worry. We just got to integrate right now, Grace, how much charge we are enclosing. So we want to make sure we understand that right now we're enclosing this charge. Our cylinder is actually enclosing this charge in it. So, yeah.
R would go from 0 to big R or like little r, wherever R is.
Yep. Mm-hmm.
Phi goes from 0 to 2 pi, and then Z goes from 0 to L.
Yes, because, and again, you will say, why from 0 to L? How do I know what this value of Z is down here? Well, again, you can very well pick the XY plane to be over here. I'm just relieving your stress there about that. And then measure Z like this, right? You can do that, and that's what Grace is doing, right? So she's saying we go from 0 to L for a Gaussian surface. It doesn't really matter, okay? It would matter if we had a Z dependency on the density. Oh boy, then it would matter. We need to be careful where we put the origin. But right now you can slip around this coordinate system and it doesn't really matter. Like the height of the XY plane does not matter. That's what I'm trying to tell you. So you can pick it to be at the bottom of the Gaussian surface if you wish. Okay, so we did that. Right-hand side right now, pulling out the constant, that's rho naught. And our integrals look like this again. We can split them. So you've got r squared dr, and then you've got your d phi, and then you've got your dz. And they're all split from 0 to r, from 0 to 2 pi, and from 0 to L. Okay, I hope you can see without me doing anything that these cancel this stuff here, right? That's literally what's going on right now. And the only remaining thing on the right, on the left-hand side, we have E times R. On the right, we have rho naught over epsilon naught, and we're integrating R squared. That is R cubed over 3. Evaluated from 0 to R. We don't even have to do the evaluation. We can see that this is just going to be this, right? And that's it. So I get rid of a factor of R here. There we go. And then we have here the electric field is equal to rho naught over 3 epsilon naught times R squared. And we've come in from the beginning knowing the direction that it's going to be in the R direction. And that's our electric field inside the cylinder, period. Okay. Now, if you want to do the outside, right? If you want to do the outside, it's the same process, okay? Up to here, if you want to do the outside. So first and second steps here are going to be the same. I'm just saving some time by copying. We're doing the outside now. And so everything is the same up to here. The electric field for the outside. Let's give you a nice little diagram to have as a reference. Obviously, on the outside, we still expect the same symmetry, right, for the electric field. So like if I go and make the Gaussian surface now a lot bigger, right, to make it go on the outside now, the cylinder, just like that. I'm going to have to be careful with my bounds now for sure. But that's not how my Gaussian surface looks like. Again, you've given this guy some random length L, right? And some radius R. You can see them both right there. Okay. Same cylindrical element applies. We don't need to see that right now. Okay. And so we go and ask the same questions. What is going on over here? So for the electric field, again, the electric field lines outside look the same, right? The same symmetry right now, penetrating the Gaussian surface at right angles, right, which is exactly what we want. So the normals, again, of the Gaussian surface are parallel to the electric field as usual. Okay. And so now that I do the outside, let's see what changes. We have the simplifications necessary again to pull the electric field outside the integral. All I need again is how big is the side of my Gaussian cylinder? So the formula that Olivia gave us before still holds because the radius of it is r and L is the length of it still. Okay, so I'll plug in the same thing, 2 pi RL, and that means we have E times 2 pi RL. On the right-hand side, though, again, we're integrating the charge density, but this time the bounds are going to be a little bit different. So we shove in the density, which was rho naught R, and then the cylindrical volume element, which was R dr d phi dz. However, now I want Kelly to tell me the bounds here. So be careful, Kelly, because you're enclosing right now. You're only focusing on what you're enclosing, how much charge you're enclosing. You are literally enclosing this that I'm trying to highlight here with red, right? Like this part. You're not going to consider the empty space here. So with that being said, what do you believe the bounds should be?
For R, it would be from 0 to the capital R. And then phi would be 0 to 2 pi.
Mm-hmm.
Z would be, it's not L, but I don't know what's the inside.
It is L. It's my bad here that I've done this. One sec. So technically your Gaussian surface should look like this. It's an infinite distribution, right, Kelly? So its length goes to infinity right now. I'm not outside of it lengthwise. It gives you the false sensation the way I did it, so I'm going to correct it. It gives you the false sensation that I'm sitting outside lengthwise. I'm not sitting outside lengthwise. This is an infinite cylinder. I can never reach the infinity part, right? So watch out for that. I'm just fixing the surface so that you see it a little bit better. The cylinder, in other words, in layman's terms, is always going to be longer than my Gaussian surface forever. So I will always enclose just what you see here. So what do you think now that I made this?
0 to L.
Yeah. Okay. So 0 to L. All right. Again, split it up. Pull the constant outside. And so we have here the integral of r squared again, dr, the integral of d phi, and the integral of dz, all going in their respective bounds. Okay, so I think you can see what the difference is. Obviously, these again here will cancel the 2 pi and the L. All right, so we got E times R and then rho naught over epsilon naught. The R integral, all it's going to give you right now is capital R cubed over 3. So overall, you can tell them the electric field, right? You can tell them the electric field as rho naught R cubed over 3 epsilon naught R. And that's it. This is also in the R direction. That's it. Okay. So what do we do over here now? If they ask you to find the potential now, you did Gauss's law to find the electric field. What if they asked you to find the potential? Okay, let me steal the diagram then again to show you this. Okay, so I'm going to delete the Gaussian surface. We really don't care right now about the Gaussian surface, but we do care about the fact that we have 2 electric fields acting, one inside the cylinder, one outside the cylinder. I'm going to call the inside one as usual. Okay, this is a refresher on potential again. I'm going to call the inside E of R less than capital R, and E here is going to be R greater than capital R. They all point like this, right? Okay, so in this side again, the lines will look like this. Okay. There we go. So you have a good picture right now of what the electric field will do on each side. So remember, this is an infinite distribution. I told you that these usually experience a problem if you take infinity as a reference. And I'm not lying. This one's another one that does this. So what am I going to do right now? If I want, let's say, the potential outside. Someone tells me, George, try to find the potential outside right now. I got to check, okay? Eventually, I will have to see if infinity is a good reference. 9 times out of 10 for infinite distributions, it's not. It's not a good reference. It blows up the potential, if you remember. So what do? I go, okay, I'll take a couple of points here outside, since I'm working outside. This is going to be my P ref. And maybe, the other one here is my actual P, like, over here. The distances, again, that they are from the center of the cylinder, respectively, this is going to be like, I don't know, R ref, if you must. And the other one here is going to be just R, the cylindrical R. Okay, and we've done this before. It's not like you haven't seen this. We did it for the plane. It was in terms of Z when we did it for the plane. So what do you want to do here? Well, again, we're working for only outside. What are we going to do? We have to fill in that integral, if you remember. So we got V at P minus the V at the P reference is the integral from P reference to P. Okay. And we have here the electric field outside, dotted with DL. That's how I want to go about this. Okay, so we know that the voltage, again, because the electric field is a function of only R, I know that the voltage is also going to be a function of R. Like, I just, again, it's just the way the cookie crumbles. You can't just gain dependencies out of nowhere. Since the voltage is dependent on the electric field, it absorbs the dependency. So that means our point P, even though it has 3 cylindrical coordinates in general, only one matters, the R. So basically, its position is basically defined with respect to R for our purposes. The other guy here, his position is R reference. And then the integral, we'll go over here. We'll put the electric field in that we got for outside the cylinder right now. Here it comes. Here it comes right there. And again, we're going to dot it with the L in cylindrical coordinates. I promise that this again will return a cylindrical dr. So the integral is running in the R direction. So of course, we're going to integrate here from the R reference up to, again, R. Okay. So we have V of R. I'll move the V reference on the other side. Oops. And then I'll subtract. Again, we're going to pull out the constants, R naught R cubed over 3 epsilon naught, whatever. Okay. We're not going to pull the R because that's getting integrated. So we have the integral here of dr over R, as you can see, from R reference to R. Beautiful. That's what remains. Bogdan, what's that integral?
Oh, that's just R.
What do you get if you integrate 1 over R? You remember?
Unfortunately not. Oh, wait, yeah, it is just ln of R.
Yes. Okay. A ln of R. We're evaluating it again between some R reference, R ref, to R. And so you see the only thing that happens here really, I can put everything in. We got a ln of R minus ln of R ref. Okay. And of course, these are going to get combined, and I'll throw the negative sign in here to flip the order around. So in the final step here, the potential is going to look like this. Once I've distributed the negative and I've taken care of the logarithm with logarithm rules, it's going to look like this. R reference is going to be on the top there. Okay, and on the bottom, we're going to have R. That's going to be a plus here. So remember what I did for the infinite line? I was like, what happens, when R ref goes to infinity? Can this work as a reference? What happens to the logarithm as this goes to infinity? Think. Olivia, if I put this to go to infinity, what does this do?
So it approaches 0 and ln of 0 doesn't exist.
Ln of infinity is 0? You sure?
Oh, sorry, no, I mixed up with char. I can't remember what ln of infinity would be. Oh,
That's what it is. So if this is infinity right now, do you think I can make any meaningful measurements with this part?
no.
No. You see why I can't use infinity right now as a reference anymore? It's broken. You can try taking another clever point here. What about if I took it at 0? Someone would say, yeah, this would work, but are we sure about that? What would happen here? What's ln of 0?
It's undefined, I believe, right?
Or if you're me, it's negative infinity. So both of these are no. You see what I mean? You can't escape that problem. It's a really annoying problem, but you can't escape it. It sucks. Okay, it really sucks. So that's what you can do here. That's as far as you can go. And the only simplification you can say right now, you can make this equal to 0 like we've done in the past. Again, you have a choice if you want VR reference to be set to 0, but you are still stuck with the reference point. You can't get away from having to use some kind of in-between reference point between 0 and infinity. It's just the way the cookie crumbles. It's up to you if you want to make this 0 or not. I wouldn't be mad if I was the TA. I know my physics. I would completely understand what you're doing. It's up to Brenda what she teaches you with this stuff. But I doubt they even talk about this problem with a potential. They only surprise you on an exam with it. So that's what you need to do. Now, obviously, if you go on the inside, it's a little bit worse than that. And I'm going to show you again what happens. So this potential function is good for the outside right now. Okay. So what if you go on the inside? Right? What if you want to work on the inside? So the P ref here could be anywhere you wish it to be. Nobody cares right now where P ref is. But when you're on the inside, both the P and the P ref need to be on the inside. They need to be in the region that you're working with, right? So here's the deal. I want to leave. I'd like to leave the P reference outside. Okay. And then, my trip would basically, again, I want to show you here what's going on. If my reference is here, let me give you a better visual, okay? Let me give you a better visual. Why am I changing the position of these? I'll explain. Because I want to show you visually here something so you understand. Let's take the reference to be here, and let's take like the point of interest to be here. So the situation is exactly like you did the spheres. This was just dragged out to infinity when you're doing spheres. I just want to show you again, it was dragged out to infinity. Now it's not. It's at some finite distance. And your trip, where we're doing this integral here for the potential, your trip is like this right now. You're going like this. You see what I mean? You just traverse this electric field for a little while, for this amount over here. When you go inside, we should maintain the same picture, okay? But P is going to be on the inside now. So I just want to show you very visually how it looks like. You have the P ref out here still. You can keep it there. Nobody cares what you take as your reference, by the way. And you make this guy right now, since you're working on the inside, you're making the P inside. I mean, it makes sense, right? This is bound to be inside. So your trip right now, let me explain. Just like when we did earlier sphere problems, your trip starts from the P reference. You see that you're integrating this electric field while you're out there. And then you come in, right? Then you come in, sorry about that. And it changes to the other electric field, right? So it's like exactly what we did for the sphere, only that the P reference is not at infinity, basically. That's it. Literally, it's the same problem, but P ref is not at infinity anymore because we can't have it at infinity. We told you we're gonna get infinities for the V reference, and we're not gonna be able to make any meaningful measurements. If you have infinity here, you're not gonna be. If this is 10, you still get infinity for this. You know what I mean? You're not making any meaningful measurements. So we don't take infinity as the reference. Plain and simple. Okay, so how do I do this integral? Again, same deal. You want to look at the potential at point P. You use P reference as your reference point. Therefore, we're going to go from P reference to P. We're going to integrate all the electric fields throughout. Now, what are those electric fields that we're going to traverse? First, don't forget that the potential is only a function of R. The value of R for P, we've labeled it as R on the diagram. The value of R for P ref, we've labeled it as R ref. So I go over here and I put in now my electric fields. When I start at my reference, my electric field is the one outside. So R greater than capital R. This electric field acts on me until, you can see here, until I hit the radius capital R. You see? Perfect. So I need to add to that another integral that continues from capital R, right, until the radius of my point P. We've done this before. It's just a little bit weirder now with the cylinder. And of course, the electric field that acts on me is the one that is inside the cylinder. We have both of them. So let me start simplifying here. V of R, we'll move the V ref on the other side again. Whoops. And we'll subtract here, again, the integral from R ref to capital R of the electric field outside, which was this bad boy over here. I'll bring him in. Boom. And again, it's the same kind of integral that we had earlier, right? With the only difference, as I'm writing here, the same stuff basically. This integral is only different from this integral on the bound. The bound is capital R this time. That's it. The bound is capital R. Everything else is the same. So you go, okay, why then don't I use the result that I had previously? So here we go. Steal this, and put it over here. So I'm just going to show you what I'm going to do here real quick. You see that? So why don't I cross out this guy and replace him with this? But that R on the denominator there is capital R. Why redo the whole integral again? I don't want to. Do you want to? I don't want to. Okay. Okay, watch what's happening here. So this is getting replaced. Now the other guy here, we got to integrate the electric field on the inside now. Okay, so we go and find the electric field on the inside. Where are you inside? Here you are. There it was. Remember this guy? Okay. So we got to integrate now this. That's the electric field inside from capital R to little r. And we're dotting this again with the L, which is going to bring us a nice little dr as a gift. Perfect. So I keep plowing through with this. What have I remained with? I have V R ref minus all of this stuff over here. The blue stuff is going in the bracket. Okay, again, this is R like that. Perfect. So as you can see, boom, boom. Okay, they go away. And now I'm wondering again, I'm doing this guy. I can pull the constants outside from him, and it's just an integral of r squared. Well, integrals of r squared become r cubed over 3. And I'm evaluating this between capital R and little r. Fair enough. So what I remain with, magically, we have something nice. We have this, okay, remaining. Okay, there we go. And then we have minus rho naught over 3 epsilon naught. Actually, that's a 9, right? Yes. Let me not screw that up. And then in here, we just have r cubed minus r, capital R cubed, excuse me. Boom. That's it. So you go again. You ask yourself, can I use this? You know, you go, can I please use this? No, because again, we will have this to blow up. We can't use that. And you can see what happens again if I try to use 0 as a reference point. The ln again goes to negative infinity over there. So we can't use that as well, sadly. Okay, so we have to leave them as is. And again, your choice is to make the V reference 0. V reference canceled though over here. And so this is your answer. Yes. That is a function again for the potential that works only on V inside. Notice that this is a constant. I don't know if you're even noticing this stuff. Like this is a constant. And you might say, why, George? Where did the V ref go? Where the heck did the V ref go? Well, this is the potential that you gain from moving from here to here, like to here. Okay, that's the logarithm part right now. That is actually the contribution of V ref. Exactly. That's it. And then the other part, the second part of the integral, tells you about this potential that you've gained. So again, this talks about the outside from P ref coming into the cylinder, and then this continues the story into the cylinder. Okay, so let me ask you something. Can I get the potential in the middle of the cylinder? Does it blow up or no? Olivia? What's the potential at the very middle of the cylinder right now?
I'm still trying to figure it out. Could you point me in like the right direction for it? So just negative r cubed?
Yeah.
Or like
Cancel this.
rho naught. Yeah.
Yeah. You cancel this guy, and whatever remains is the potential at the center of the cylinder. There we have it. So that's what it is. That's a typical problem for cylinders. I don't know if it's likely they're going to ask you for finding specifically the potential, but they will ask you for the electric field. I put my hand on the train track. They will ask you for some kind of cylindrical electric field, whether that be a solid cylinder, concentric cylinders. I don't know what the contraption is going to be, but be prepared. That's a solid cylinder over here. You can take it as a solid conductor if you want. Actually, no. That's a solid insulator that we just did. Solid conductor would only have the charge on the very outside, right? So that's the problem, and it's a complicated one, okay? Potentials are not very friendly if you're in first year. I'm sorry about that, but they're not very friendly as a concept. Any questions though? Anything I did that was questionable and it didn't convince you? Do you understand the reference point and how, like, for finite charge distributions, I can put it at infinity, but for infinite charge distributions, well, things break, right? And I can't use infinity or zero in this case. I was trying to get rid of the R reference, but no, you just can't.
I don't understand, like, when we did the Gauss's law,
Yeah?
why you said it is dependent on R? Like, why do we need to integrate the Q enclosed?
Because the charge density here varies. So every shell, every cylindrical shell that you integrate will contain a different amount of charge because of this. And so it needs integration instead of simply a multiplication, right? You need to think of it as adding up little shells, and each shell will contain a different amount of charge, and you have to integrate that. Versus if you had a constant charge density, you could just multiply the density by the volume of the cylinder and get the charge enclosed. It's a very different process here.
Oh, okay.
Anything else? Okay. All right. Long problem. Okay. But again, that's what I wanted to do. I want to move into something like this, okay? Because this is guaranteed. I can feel something like this coming on your midterm. I mean, look at it. And
Well, yeah, I
it's-
think that one they confirmed is definitely going to be on the midterm, like 20 out of 90 marks.
Right. And you can see here what's going on, right? Like, we have a mix of like conductor and insulator. So it's beautiful as an example to mess with you, you know, and then like try to see how we can detangle the mess here. So it says, be careful again how you deposit and where you deposit charges on conductors, because we said things are going to react, right? They're going to change polarity and etc. So an otherwise neutral concentric shell of inner radius A, middle radius B, and outer radius C is filled with insulating material that carries uniform charge density rho. You can see the yellow is the insulating material, okay? And it has a charge density rho because it's a volume, right, that contains this. Okay. So it contains rho between A and B. You can see here how I've drawn it. It's between A and B, the insulator. Okay. Now, the space between 0 and A is solid conductor. Between 0 and A, solid conductor. That's what you see here. And then they go, or I go, because it's my problem. While the space between B and C is hollow. So again, between B and C, you can see here, air, hollow, nothing. Determine the electric field everywhere, the electric potential everywhere, and plot it. I'm not going to plot it, but we're going to determine both of these quantities. I hope we're ready. Let's roll. Grace, what kind of Gaussian surface would work here for this kind of symmetry? What would you use to do the electric field? What kind of Gaussian surface? Concentric spheres. Can you hear me, Grace?
Oh, yeah, sorry. What was the
Okay.
question?
So what kind of shape would we use here for Gauss's law if we have a sphere?
A sphere.
Okay. So I need to start again from the very inside. So I'll start from the very inside. Now, you might be thinking, George, there's charge here and it's touching this inner conductor. Shouldn't it be like spreading onto it right now? Well, the answer is no. And the reason is, again, because that's not the largest surface area. That's not where the charge wants to go right now. Also, I should be careful to mention that the insulator over here and the conductor are arranged in a way that they're, again, the charge from the insulator is not leaking into the conductors. They're not really touching or anything like that, right? I know it's hard. My diagram doesn't really convey that, but if you were touching, for example, all of your charge here would just move to the outer bits over here. It would just move to the outer bits. Now, we can solve the problem in that fashion. I don't know if it's going to be of interest to you. So sometimes, again, you have a charged insulator here neighboring with an insulating sheet here. Like there's a sheet, for example, that keeps the insulator and the conductor separate, right? So they don't touch, and you don't get the charge to leak onto the conductor and go and spread out, right? That's what I'm trying to say here. Like there's a little bit of an air gap. There's a little bit of an air gap between the insulator, either air gap or some kind of another insulator that's not charged like that. And it's just, preventing the charge from leaking from one place to another. Okay. They would tell you if otherwise. They would tell you if like these were touching. You can ask on the midterm if you're unsure. But we're not having charge leak right now into the conductor. However, you'll see that the actual result for this area here doesn't care about that. The only result that would change if they're touching is that the charge here would dump itself onto these conductor plates and the charge here would be zero. So it would be this area here that would have no electric field right now because all the charge would just migrate to the conductor here. That's it. There's no other difference. Everything else would be exactly the same for all regions. So let's solve it for the case that, again, they're not touching. They're segregated, okay? And you have that Q in here. So you go, okay, how can I do this? Well, let's start from the very inside. It's very easy to see what will happen for the very inside for R less than A. Well, can you tell me, Kelly, how much charge I'm enclosing if I'm on the very, very inside there, like inside the radius A? So we're in here right now, okay? The actual charge is here. It's going to cause reactions on these plates, but on the inside part, it's not going to cause a reaction. Because why? You might be wondering why. Because the electric field made right now by this yellow part is going like this. It's not going inwards. It's going like this, okay? And it's going to induce charges over here, negative soldiers right now on this surface, like that.
So sigma dA.
Okay, be careful. The inside part is solid and there's no charge on it right now.
Oh, so 0.
No charge, and therefore the electric field there is 0. Okay, but of course, when you move between A and B, things are changing. So what happens there? Well, I have to write Gauss's law again. Let me grow the sphere so that you see it a bit better. So our Gaussian sphere is going to be like over here right now. And I'll give you again its radius, maybe with an orange line right there. Okay, so that's the radius of our Gaussian sphere right now. I'll make it pink actually to match the sphere. That's R. And you can see again that we can do Gauss's law. Here we have the symmetries required with the shape that we're using. So we write down Gauss's law real quick. The density is uniform. We'll figure out what that density is in a second, but this side satisfies all the simplifications that are necessary to write it like this. Whoops. So, Olivia, what is the surface area of the Gaussian sphere right now?
So I might be misremembering it. Isn't it, oh, what was it? Surface area, so r squared. I'm tempted to say 4 pi r squared, but I think it's different. Oh no, like that's good for spheres.
Mm-hmm.
Okay.
So that's our surface area. And on the other side right now, we have to, again, I'll ask Kelly, how could you get, I'm giving you a hint, Kelly, how could you get the charge enclosed right now? Be careful. The charge enclosed right now only exists here. We have a constant charge density, but even if we do have a constant charge density, I always encourage you to write this as an integral, because you might not sometimes. But what did we multiply together last problem to get the charge?
Explain two things are adjacent. My word.
So I want Kelly on that.
Do you do like rho v?
Rho dv, yes. Okay, so this time around, the rho is constant, so you can pull it outside, right? And Kelly, I only need the volume right now, the volume of the enclosed charge. Look where the yellow shade is. Like, actually, let's make it a different color so it pops. Maybe red. Look what I'm shading here. That's what the charge is that you're enclosing. So what could you do to find the volume of this region? It's 2 concentric spheres here. One is the pink one. Okay, that's the pink one right there. And the other one is the one that has radius A right now. What could you do to find the volume between them?
The bound is from A to small r.
Yes, we could integrate the dv from A to small r. Alternatively, we could take the volume of the outer sphere minus the volume of the inner sphere, right? You remember the formula for volume and spheres?
R squared minus a squared sine theta dr d theta d phi.
Okay, that's the dv for spherical coordinates. Do you remember the volume of a sphere, the formula?
Oh, 4 pi r squared over 3.
It would be r cubed, but you're right. Okay. So you want to, again, factor the 4 pi, the 4 pi over 3 outside, and basically have the outer radius right now, which is r cubed, minus the inner radius, which is a cubed, and that would be right now your volume, the enclosed volume. That's it. That's what we need to plug here. Okay? And I don't want to do the integral. Whenever I can avoid an integral, I will. Like, I don't want to be integrating for no reason. We don't have a function that we need to integrate. We just want that volume between the spheres, right? And we can find that without integrating. So we have over here, we put it all together. You can see what's happening. We got 4 pi rho. And again, before I continue, let's ask Kelly again. Kelly, what is this rho right now? Okay. Are we given rho? Let me see here. Okay, so we were given rho. Never mind. We don't have to determine rho. Never mind. So we have over here 4 pi rho. okay? R cubed minus A cubed over 3 epsilon naught. And of course, some of these things drop. And we basically get the electric field now. It's going to be rho over 3 epsilon naught, R cubed minus A cubed over R squared. And this is all in the R direction. We walked in knowing again this. That's the electric field in that region. Okay, so that's between A and B. Now I want to do, of course, the other region over here. So now it gets interesting. Now it gets very interesting over here. I'm going to delete that stuff. You don't need it. Okay. So obviously the radius of the Gaussian sphere is growing. Now, so we got a bunch of negative soldiers here piling up because they're trying to stop the electric field from the positive charge that's enclosed, right? That's what's going on right now. Remember, we have like induced charges on that inner shell here that are negative right now. And these negative charges leave behind positive holes. The positive holes migrate over here on the opposite side of that conductor shell. So they're chilling out over here. Okay, now how much charge should be on each of these plates here? That's what we want to figure out. Can you, any of the four of you, can you guess how much charge should be right now in this, in each of these shells? Take a wild guess. My hint, if you want to hear my hint, the total charge that is in here is going to be some value, rho times the volume of this area. Okay, so we're going to have some Q from this rho as a total here, like in the insulator. That's my hint. Let's call that charge Q that's in the insulator total. Who wants to pick it up? What do you think? There's an army of charges that amounts to Q, and I'm trying to stop them. What's logical here? How do I stop the army?
Is it like one positive or one negative charge?
Yeah, in total though, like the total Coulomb amount, how much should I have on these plates, on the pinks?
Q?
Q, yeah, exactly. So I have negative, I have negative Q induced on the inner plate here and positive Q induced on the outer plate over there. Okay, again, I'm going to make sure you see that this amounts to Q over here, the total charge on the insulator. Even though I don't have it, I can find it. And I think Kelly can also help me find this charge, actually. So Kelly, what the heck is this Q right now? How can I find it, having the density?
Rho and times volume.
Times whose volume?
The Gaussian surface.
Not quite, but over here, do you see where the Q is contained? It's contained here. That's whose volume we want to multiply the density by to get the total charge enclosed, right?
Yeah.
How would you write that down? So let's again recuperate here. So we have to do rho times the volume again over here. And we're asking, what is this volume? It's two, again, an outer concentric sphere and an inner concentric sphere. And we're looking for the volume in between them.
So 4 pi the big B minus A cube over.
Yes, and I want everybody to see that. So she's doing B because that's the radius here. And then she's subtracting the volume of this guy, which has radius A. That's what she's doing. Those are the concentric spheres that she's subtracting. So she's doing B cubed minus A cubed. And of course, don't forget to divide by 3 here. That's it. That is your Q right now. Okay, so now that you know this, you're in a position to solve the rest of the problem. Let's see how. So when we are between B and C right now, we still write again our Gaussian law over here. But for the right-hand side, it's really easy right now to find Q enclosed after what we did. Let me ask Grace. Grace, you're out here with a Gaussian surface, and I just want to ask you, how much charge are you enclosing underneath you right now? Look at all these charges. There's no extra hiding stuff.
You'd only be enclosing the charge between A and B, right?
And we got it. That's why I made
Yeah.
Kelly get it. We got it over here, right? So might as well just write it out. And like I told you, these induced charges never really contribute to Gauss's law. They always cancel out, no matter what happens. Even when you do dielectrics, this is true. So we only have here Q over epsilon naught. And I'll get back to this Q. The left-hand side is as you expect again. We just have to put down the area of the Gaussian surface, which is still and always will be for this problem, 4 pi r squared. So, we're coming in. Got a 4 pi r squared in here. We got the 1 over epsilon naught here. And then what Kelly said. So rho 4 pi over 3 E cubed minus A cubed is the charge enclosed.
Wait, George, I have a question.
Yeah.
Okay, so there's no E field inside a conductor, right?
No. So over here, no E field.
But if like the E field goes through a conductor, then does the E field like come back again?
If the E field goes through a conductor,
Like the concentric spheres are conductors, right?
yes.
Yeah, so the E field is like going through like the second concentric sphere and it's like going out again.
Oh no, it's not, Grace. So like every thin material, like the concentric spheres here, it always has like a little bit of thickness, right? And basically through the conductor, you don't get the electric field to cross. It doesn't cross the double blue lines here. Okay, it is 0 on the actual, like the little volume, I guess, if you want, of the concentric sphere here. It's actually 0. And it's the same here too, right? So again, I'm saying that no matter how thin you make the surface, okay, like that makes up the shell, it will always have a little bit of thickness, right? And we're saying that the negative charges here pile on the inside surface and the positives on the outside. And in between here, no field lines exist. They can't exist. That's what's going on.
So are you saying that the E field going out of the conductor is from the positive charge on, like the positive induced charge on the conductor?
You can think of it that way, right? You can think of these two canceling. You can think of it as these
so
two.
positive Q left, and then that's where the electric field lines are coming from?
Yes,
Okay.
technically, if you want to draw the electric field diagram. But when you're doing Gauss's law, I just encourage you, whatever is labeled pink here, to just automatically not consider it, right? So it's a matter of perspective. If you want to draw the electric field lines and you're wondering where they're coming from, these basically cancel. They're coming from this. They're coming from this charge density being on the outer surface of your conductor sheet. Okay, but in between the sheet, no electric field over here. Sometimes, again, people don't even include double lines for this. I do to show you the induction that's taking place, but sometimes people don't even do this, okay? But it's nice to do as an exercise, as a principle, because there is induction going on here. So, of course, you include only the Q. We know what the Q is. We've put it in. You can see some cancellation that takes place right there and right there. So what remains here is a 1 over r squared dependency, which is what you expect. And you've got here, let's write it all down, b cubed minus a cubed rho. Okay, and then 3 epsilon naught r squared. And the direction is radially outwards. That is the result in between. Now, the magical thing is, you'd think that this will change, right? Like as you're moving outwards, but let's see what happens actually. So you have an electric field and it's emanating again in this direction right now. That's what we just figured out, okay? A lot of electric field. Let me just draw 4 lines to represent it. So there they go, okay? And now I'm wondering again, what happens outside the entire contribution, like when I'm out here. So I grow the Gaussian sphere even further. And its radius right now is going to be whatever this is, just r. And so you're wondering right now, what's going on outside? But then if I ask you guys again, look what the charge underneath you is right now. It is just positive Q. How many charges do you think I should pile up along here to stop the electric field again?
Negative Q.
You see that we have a repeating situation of the inner shell? Like it is exactly the same deal. So I'm just going to put them all here. So the inside surface again obtains a negative charge density right now. It's uniform, even if it doesn't look like it from my diagram, because I didn't draw it exactly. So it's uniform. And the holes that have been left, the charges again, the ions that have been left from those electrons migrating inwards, have migrated on the outer shell. They don't like this electric field. They want to go away from it, but the electrons are attracted to it. So as you can see, the situation essentially repeats. You've got here a negative Q and an induced positive Q on the outside. And then when you're asked about, watch this, when you're asked about what's the enclosed charge under the pink sphere, what do you say now? How many Qs do you see? Add them all up.
Still the yellow Q.
So in fact, what you did here, okay, works also for R greater than C. In fact, what you did here is for R greater than B right now. Forever, this is your electric field afterwards. Now, yeah, you can say there's a discontinuity on the conductor at R equals C. Yes, there is a discontinuity there. But again, the conductor sheet doesn't have any extent in R. It's not a thick sheet, so we don't really even see that over here. Like this thickness here is basically 0. We just have it here to display the separation of the charges, right? It's not there. It's not a physical width right now. Okay, so we don't really consider that. Yes, the electric field in between here again is going to be 0. But there is no width to these plates, so I'm not really considering them as a separate region, right? So there you go. We skipped a step because we saw that the enclosed charge doesn't actually change when you're moving outwards. It stays the same. It's still just the real charge that you have on that insulator. Isn't that incredible? And there you go. There you have it. You now have the electric field everywhere in space. Okay. And again, I need to put the lines here to show you. This just continues on doing its thing. And I'll delete the Gaussian surface. We don't need it anymore. That's what's going on. So those are the electric fields. You want to find again the potential everywhere if you wish. So since this is a finite charge distribution, it's has a finite extent, we can use again infinity as a reference. So again, I go over here. I always start on the outside. I'll always give you a diagram as well to see what we're doing, but I always start on the very outside. Okay, so I'll put the diagram here again. I want you to understand that I basically have three electric fields right now that or actually, three electric field regions. So we got our E. Let's call this bad boy here E greater than, for R greater than B. Let's call this one between A and B. And let's call this one R less than A. So you got three electric fields that you could possibly traverse right now. All right, so that's understood. If we're doing the very outside, again, okay, R greater than B, that's our first region that we investigate. Okay, well, that means we're somewhere, we could be here, by the way, we could be here because we're just anywhere, you know, after the radius B. So I'll choose the point to be here for clarity. And I want you to see that I'm coming in from infinity. That's our ref from the previous problems. It's infinity. My path, here it comes, okay? That's the path that I take. And I'm gonna start my integral. V at point P minus V at point reference right now is equal to minus the reference point, the point P of the electric field I traverse. Okay, now, again, because the electric field is a function of R, so will the potential. That means the position of point P, we only need its R component to define the potential. We don't care about theta or phi. So for the reference point, we took infinity to be the R, and we know that the potential there is 0. That's what happens for finite distributions always. And then we're integrating the electric field on the very outside, we said. So the electric field on the very outside, let me again indicate that we're doing that. The electric field on R greater than B, dotted with the L. So I'm gonna go fetch that. Here it is. Okay. All right, so there we go. We dot that with DL. That gives you a nice little DR. And so we're traversing here. We're going from infinity, which is a reference, to the point R, which is the point of interest. There we have it. So V of R is minus, again, I'm just gonna copy the constant outside the integral, speed things up a little bit. And the integral is dr over r squared. This is, again, very familiar. This just gives you -1 over r for the result. So the potential is basically just this constant right now. You can see what it will become. So just this constant.
Wait, is it like b cubed minus a cubed?
Yes, I think I lost it in the copying there. I hope not. It wasn't. Yeah, I lost it in the copying there, Kelly. Thanks for noticing. So the integral 1 over r again, we've seen this a million times, going from infinity to r, negatives cancel. And all you're left with is a 1 over r dependency, which is what we expected. Here come the constants, rho, and then 3 epsilon naught times r. So this is the function, again, that will work for any point at r beyond b. Any point r beyond b, use this function to find the potential. Okay.
I have a question. So what about C?
It doesn't matter, Kelly, because the electric field right now, even if I was here, even if I was like in here right now, and I'm coming in from infinity, I am encountering, let me show you. So as I'm coming in from infinity, it's the same electric field out here and the same electric field in here too, in that region. Remember, we just proved that when we're doing the Gauss's law. So the electric field here and here, they're the same thing.
Oh, okay.
It's the same electric field. So I know that we're getting interrupted by the conductor. But again, we said that the conductor doesn't have any extent in the R. So we don't give it its own region to say that between like 5 meters and 5.5 meters, we don't have electric field. It doesn't have significant width at all.
Is it because of the Q charge? Like,
What is because of the Q charge?
like we don't do C, the region C, because of the Q charge? They're the same.
Well, we showed why over here, right? So when we had the Gaussian surface outside, we enclosed these 4. So these canceled, right? And when we had this region, like the Gaussian surface was here, we enclosed these. So again, we had Q enclosed equals to Q. So the results match. The results match for here and here. So you get the same
okay.
electric field.
Okay.
All right. So again, our trip here, I'm putting the point P so you see here that it doesn't matter if it's like, if I put it here or I put it here, it doesn't matter. So for that region, this is the potential. Now, if I continue my trip on the inside, things take an interesting twist. Okay, you know how to deal with this, but I will show you nonetheless. Okay, so now the point P is in here right now. Okay, it's there. And so the trip breaks itself into 2 parts. The first electric field here, and then the second electric field there. Okay, and point P again is some distance r from the center of the sphere. Some distance, I don't know, from the center of the sphere. 1 second. Let's put the point P there. Okay. So now that I have that done, let me make sure you can see that goes all the way to P. All right. Same deal, right? You start again writing it out. We're doing right now for the region between A and B. V of R, V of P minus P reference, V of P reference is equal to, we're going to go from P reference, which is infinity, all the way right now to the shell. R equals, I guess here, B. We're integrating this electric field until we get there. And then we continue from that shell, so from R equals to B, to the point of interest over here. And we're integrating this electric field now until we get there. So again, I need to bring in my electric fields. So the R coordinate of my P reference is infinity. Again, I go up to B, and the electric field outside, once again, is this guy. So, you know, I can rewrite them. I don't know how much detail your professor will want to see, but I would show this right now. And again, this invites a dr. However, if you pay close attention, this is the same integral as we had before. Again, if you see It's the same exact integral as we had before. I can put them both on the screen. They're exactly the same, but the upper bound is now b, which means I can steal the result from here with the substitution that little r is b. Okay, that is literally what I can do here. So this is basically what you see here with the substitution that this becomes b. There you go. Recycling again the results from before. Why not? So the only interesting one is the next integral, which we haven't done yet. And this one goes again from B to the point of interest. The electric field between A and B is this bad boy over here. We have everything nice and organized to integrate. So I'll go over here and put it in. There we go. We're dotting this with dl again, and this invites a dr. Okay. Now, on the left-hand side, the position of P again is defined by little r. The position of P reference is infinity. The voltage at infinity is 0 by definition. Okay, so we got this remaining. Well, let me continue on this step in a fresh manner. Okay, so we got, b cubed minus a cubed, yada, yada, rho over 3 epsilon naught b. And then minus, if we pull outside the constant here on the second integral right now, I would split this integral into two parts. The first one, as you see, I would distribute the r squared into the r cubed to get myself only an r dr. And then I would have another piece here where I would pull the a cubed outside and I would be integrating basically 1 over r squared this time. The bounds are the same from b to r, from b to r. You can split integrals like that, because they're just polynomials right now and it's nice. Okay, so you have that ready. What do we have left then? Inside the bracket, we have r squared over 2 minus the integral of this guy, negative 1 over r, right? That's the integral of that guy. We're getting multiplied by an a cubed, okay? And the negatives here are going to cancel. So I'm just going to write immediately this. Okay, why not? Because the negatives will cancel. I explained why we're doing that. And then both of these are being evaluated between B and R. So in my next step, I do the evaluation, of course, and I'm only going to have, we're going to have a big constant pile up. So when I evaluate the R in that integrand, we basically get a repeat of this. And then when I evaluate the B, I get a nice big constant, right? So I go minus B squared over 2, and then plus A cubed over B. That is your potential function right now. And the dependency is here, as you can see, and here. There we go. So yeah, it is long, it sucks, but so is the nature of these problems with potential. Sometimes they get like this. To finish it off, you need the potential for points, again, inside the very center. You go, okay, what really changes right now when you move into the center over here? What really changed? Well, it's the position of point P, right? We're in the middle now, in the middle conductor. We're not in the insulator. We're like inside the very, very last part. But you know what's a blessing here? We don't have an electric field in there. Like, there's no electric field that we're going to go against right now as we enter the conductor, right? Let me again try my best to keep these straight. So that's the R variable, and that's point P. So yeah, you're coming in, but you know, you don't have anybody to integrate once you reach here. There's nobody left. There's no electric field in there. So essentially, the last integral for voltage is a repeat. Save time here, that's why I'm doing this. It is a repeat of everything that you've written here right now. Okay, let me explain. So everything that you've written here, I don't want to rewrite the whole thing, right? But then you have one more piece to it, which is the very inside part. Be careful though. The second integral now doesn't stop here. It goes all the way to the r equals a radius. And then we change region one last time here. And we go to some random r inside the middle conductor. But again, like I said, there's no electric field in this region, which makes this integral null. It makes it 0. Okay, and as you can see, if you were to compare what I'm writing here to here, okay, just look. If you were to compare what I'm writing here to here, look. The only difference is this bound. You know what that means? Who's going to tell me what that means? I think I've made my point now. Who's going to tell me what that means? How can I save some work here? Do I have to redo the integrals? The integrals are exactly the same, besides the fact that this was the running variable r, and this is now constant. What should I do? What should I do? The integrals are the same, but the upper bound. Place what?
Replace R with A?
Exactly. I don't have to integrate anything. You just steal the previous result, okay, and just plug in what that r is equal to a. Okay. So I'm gonna cross that out over here completely. I'm gonna show you again how it was done, so you're not confused. Okay. How did that happen? Oh my God, what note? There. Okay. So I'm gonna show you over here that basically I'm crossing this out, both of these, and essentially I'm replacing it with a previous result evaluated at a. You see? And then, of course, the V reference again is going to be 0. We don't have to rewrite the stuff. And this is going to be, you know, V of R. So V of R for the very, very inside conductor, it has no R dependency, ironically. It's just a V. It's just a constant, as you would expect, right? I'm not integrating anything. So I'm not gaining any additional potential. I'm not integrating any electric field anymore. So of course, inside the very middle, the potential is going to be maintained the same. It's going to be maintained to this constant right now. I'm guessing here we can do a little bit of cancellation. So that is going to be like, what is that? A squared? Yes. And the other one is a squared over 2. So the two of them here become 3/2 a squared, I guess, when you combine them, right? Just a big, massive constant, literally, just a massive constant. Don't be afraid of it. It's just a big number, but that's the number. And yes, you can simplify it, and I've done it in my solutions, but who's going to sit and simplify this when you're writing an exam? Just toss it and leave. Who's going to sit and simplify this? Do you really want to? You know? It's a constant. We understand it's a value. I don't know what it will be, but it's constant. Move on. So again, constant. No R dependency. So you can put that point wherever the heck you want on the inside surface here, on the inside sphere, and the potential is the same everywhere because there's no electric field to be integrated. You move around in that sphere for free. And there you have it. You have all the potentials now everywhere. And I really hope this is a good grind on potentials right now. Definitely. You have the potentials everywhere on all three of these regions, which I'm happy to show you how they're done. So what changed again in the previous problem? What was different in the cylinder? The only difference was, once again, that this was not at infinity. I put it somewhere finite. This RF was not infinity. And when I was working through the problem and I got my result, I had the option if I want to set this as 0. Why do I have this option? Because potential is relative. Just like height is relative, speed is relative, everything in physics is relative. So, you know, if you want to measure the height of this water bottle right now, okay, I'll put it on my hand like this, okay? Hold on, I don't screw it up. I'll put it on my hand right now. And you have the option, okay, of using the bottom of my hand as the reference right now, or using the floor right now that I'm sitting on as a reference. So if you do that, let me explain again how these things work. You have the water bottle, okay, and you're trying to measure its height. What is this height? You go, okay, I can use right now the floor, right? And the floor, the water bottle from the floor is going to be like some distance, let's say h right now. Okay, so let's say, what's this position here? The bottom of the water bottle, it's going to be at 0, at let's say y equals to h. And the top one, again, the top guy, let's say this is going to be y equals to h plus some distance d, right? That's going to be the initial, that's going to be the final. So if you want to find the change of your height here, right? What is it? It is y2 minus y1, or h plus d minus h. And you notice how you get what you expect, right? Similarly, if you want to measure the water bottle's height, but you take this to be the reference, now y1 is equal to 0 and y2 is equal to d. So the actual change of height here is simply y2 again minus y1, or d. You see that we get the same result regardless of where you guys put the reference. It's the same with voltage, okay? So what I'm saying is, with your voltage right now, you have the option here of setting this equal to 0. Why set it, for example, to 1,000 volts when you can set it to 0 and make your measurements with respect to that special point, wherever it may be in space, right? Make that as your 0 and make your life easier from having to carry around this stupid constant, right? It's up to you. So in relative differences in physics, the offsets never matter. Whenever you're doing a delta in physics, doesn't matter where the offset, how much the offset is. You're going to see that when we do capacitors. We're going to be looking for delta V. And no matter if you pick the top plate to be 0 volts or the bottom one, you're still going to get the same delta V. It's just, you know, an offset that gets canceled out all the time. Offsets get canceled out when you're doing differences in physics. They don't matter. They matter when you're doing absolute values. So right now, if I was to say, where is the bottom of the water bottle? You would say here that it's at H, and you would say here that it's at 0. That is a different thing. But if I was to say, what is the difference in height between the top and the bottom of the water bottle, then we all agree that it's going to be D. Because this here is an absolute quantity. This delta H is something that all observers agree on. Everybody will agree how long this is, right? But the level of one of its pieces is something that we will disagree depending on our offset, on our reference. If I take this reference, we will measure something different than the guy that takes this as his reference, right? That's what I have to say. Think of potential the same way as measuring changes in heights. You can set some height to 0 and do your measurement from there. You can set some potential position as 0 and do your measurement from there. Okay. All right. Now, because I've done a slab problem, I think it was with Kelly and I think it was earlier, and you have access to it. You know, you can search over here in the week 5, 6 stuff. I'm sure it's somewhere over here. It's probably here, actually. We've done a slab problem. There it is. So prioritizing again the things that I have not shown you, right? I would go over here and do this one, not the bottom one. This is method of images. So you said it's not like on the curriculum. So I'd do this one right now just to show you what the heck is going on, okay? So you have 2 spherical conductors. These are their radii, and one carries a charge Q1, the other one carries a charge Q2. Okay, so in the beginning, the total charge is the sum of these 2. We can agree. You just sum them together. Okay, so you have that in the beginning, but the thing is that you're bringing these closer and closer and closer together. We're going to make them touch eventually. So when they see each other right now, okay, when they see each other, because they're like charged, okay, the electric field lines that come out of them, they diverge, okay? They try to diverge like this. They don't like each other. You can't have electric field lines cross. We have something like this. And, you know, for the ones that don't diverge, I'll show you how you can think about it. I'm trying to keep my lines, remember, perpendicular to my conductor surface. That's a rule of thumb. I already have messed it up because I'm bad at drawing. There. Okay, and the rest of them are similar. So they get like a blow. I think of this guy as blow drying the electric field lines of the other guy, just blowing them backwards when I'm doing this. It's like a wind over here that's going this way. So whereas when they're alone, their electric fields would look like this, right? When they're alone, they would look like this. Now when they come together, this guy's electric field lines get blow dried toward the left, okay? So we have a situation that looks like this, dragged to the left like this. I don't know, I'm just trying to make it more friendly to you, like how you should think about it. And it's the same for the other guy. His get blown dried this way from the other like charge, right? So we have them go like this. Maybe not so much like that. You can see always being careful to make my 90-degree angles there. So that's how they look like when I bring them closer and closer together, right? That's what they look like. Okay. So what happens now if I touch them, right? That's what the problem is going on for. So they go, okay, I'm going to touch them right now. Can anybody guess what's going to happen here? Okay, how do we, okay, what about if we do this? I will make the diagram here touch right now, and I just want you to think about what's gonna happen. I'm gonna take a very quick washroom break because I'm probably not gonna last until 9. And I'll come back. Just think about right now, what should happen and why, okay? These are positives. For the sake of discussion, allow the positive to move without us discussing the negative charges. Let's suppose that the holes, the ions, are moving here instead of the negatives, okay? For the sake of discussion and making the diagram quick, let's say that the positives move. But remember, it's the electrons that cause all the problems in your conductors. It's not the positives. So keep an eye on that and make an argument to yourself. I'm going to be missing for like 1 minute. Just tell me what you think is going to happen, okay? I'm going to pause the recording. Let me hear ideas. Are the charges going to stay in place? Are they going to move? What's happening?
My guess is that they're going to repel, and like all of the positive charges that are concentrated around the edge will try and move away, like opposite sides.
Yeah.
And like E field lines would be pushing away a lot.
Okay, they are touching. So there's a bridge here, which they can use to migrate from one place to another. And I want to remind you here, one of just the rules here that we've said about conductors, right? And I was like, I gave you 3 rules over here, if you remember. So I said, inside a solid conductor, no electric field, we know that. All conductors are equipotential, so the electric fields, hit the conductor surfaces at 90-degree angles, we know that. But look at the first one. The ions configure themselves in a way that minimizes the average interparticle potential. So that just means that they spread and they make use of all of the available surface area. Now, if I go back here, I don't know the exact amounts of Q1 and Q2. Q2 could be very big. Q1 could be very big. I don't know exactly, again, the relative scale of Q1 and Q2. But let me tell you something. When they were separate right now, can somebody tell me what is special about this surface right now, according to rule number 3 that we were seeing here? According to rule number 3, what is special about that surface? What does it say, number 3?
It has like all perpendicular E field lines.
More so here. Kelly, what does it say?
Equal potential.
So when we go here, what do we understand the surface to be?
It has the same charge.
Same potential all over it right now, all over it. I can call that potential because it belongs to V1. I can call it V1, okay? Just call it V1. And it's the same principle for the other guy right now. His potential is V2. Some other value, but V2, okay? What is V1 and V2? You might be wondering, what is it? Well, I can do this on the side here for you to refresh your memory, but the way I get this, what V1 and V2 are, I'm thinking of these isolated right now, and remember this, RF going to infinity, and I'm asking myself, how much potential do I gain to come and meet this guy and kiss him on the surface here? I'm only going against this radial electric field, which I think you can tell me what its form is going to be right now. I'm really confident that you guys know what this E field is outside of the conductor. Can anybody tell me?
KQ1.
Over?
R1.
Over, well, we don't want it exactly there. We just want it outside the sphere. So just R squared here. And so, when you have this electric field and then you're trying to find the voltage, right? If I do the integral for the voltage, you know what I get here for the result here. You've seen it before. I'm just going to write it down. That's what you get. And so I want to find what the potential is exactly at R1. What do I need to do on the right-hand side? Yeah, I want to find exactly what the potential is at R1. What do I do on the right? What's the only thing I got to change on the right?
Radius.
Yeah. So the potential in that surface is sitting at this value. You see? And it's the same for the other one, right? Because they're both spheres with some charge. This is KQ2 over capital R2. That's my potential here. And the same thing here. KQ1 over R1. Okay, so the answer to the question that I was asking you is, okay, so what happens next? Okay, so depending on which of V1 and V2 is larger, the charges move accordingly. The charges move from the higher V to the lower V, and make use of the shared available space. This is what happens next. You see? So, what does that mean? That means we're going to see some shuffling over here, right? We're going to see some shuffling. Charges moving again around over here. We don't know exactly how they're going to go because I don't know exactly the value of V1 and V2. If I did, I would tell you. But overall, what's going to happen is that these are going to use all of the available space here, right? They're going to reshuffle, okay? And usually it is the bigger sphere. If the charges were similar, Q1 and Q2 were like identical, it would be the big sphere that takes more charges in right now. So we'd have something like this. So they uniformly distribute on these conductor surfaces like that. That's what's going on right now. And they do that. This stops, okay, this stops when V1 prime, so the new potential of the left sphere, is equal to the new potential of the right sphere. That's when they say, you know, when they say conductors have achieved equilibrium in your problems, this is what they mean. That the potential, you know, when you touch things or when you made a change in your system, it means that the potentials right now equilibrated. If you touch something, they became equal, right? The changes have stopped happening. The potentials have stopped changing. That's when equilibrium occurs. Okay, so right now we can tell that the charges are gonna be different. This is gonna be Q1 prime and Q2 prime, but together, right? Together, these two, if I was to sum them, shouldn't they give me back the original? What do you think? Yes or no? What do you think? Shouldn't they? Yes or no? Did I lose any? Grace? Olivia?
I'm not really sure. Like, I know it's supposed to be equipotential, so they should balance out.
Did you see any of them get annihilated? What did they do? They just went around.
Yeah, like they just disperse.
Okay, so what should these be adding up to?
What was it? Like the total.
The original, right? The Q total.
Yeah.
Okay. All right. So we haven't changed, okay? And this is called charge conservation. This is something you might need to use if you're doing a problem like this. Charge conservation. Okay. Awesome. So that means right now that Q1 prime plus Q2 prime is equal to Q1 plus Q2. And I can isolate for one of these unknowns. I don't know any of the primes right now, and I desire to know them, right? What else is there right now? Well, we said that the potentials are going to be the same, right? And V1 prime over here is going to be KQ1 prime instead now, divided by R1. And V2 prime is going to be KQ2 prime over R2 this time. So we're saying, you see, that we have to equilibrate these potentials right now. Okay, that's going to give us the second relationship that we need to solve the problem. So KQ1 prime over R1 is equal to KQ2 prime over R2. The K's drop. And do you see that I have again a relationship for Q1? It's just going to be the ratio of the radii times Q2 prime. And this makes sense, right? If the actual spheres are the same size, each one is going to take an equal amount of charge. Like, because, you know, each one is providing the same space for the charges to spread, right? But if one sphere is bigger than the other one, it's going to take more charge in to maintain, again, for the charges to maximally separate. It makes sense what we're seeing here. So let's call this equation 1. You can see where I'm going with this. Equation 1, equation 2, let's equate them. So we have, of course, Q1 plus Q2 minus Q2 prime is equal to R1 over R2, Q2 prime. We're almost there. So as I'm doing this equation, I will be able to fetch you right now what the charge on the second conductor is. Okay, so if I go here, I have Q2 prime 1 plus R1 over R2 equal to Q1 plus Q2. And I can cross multiply before I divide both sides so that I get R1 plus R2 over R2 equal to Q1 plus Q2. Okay. Let me move that problem a bit lower. Okay. As you can see, Q2 prime, the charge that I'm now going to have on that conductor, it's going to be Q1 plus Q2 times R2 divided by the sum of the radii. Now, does this make sense as a result? Let's see. If R1 plus is equal to R2, what happens? Well, you get here that you're going to have Q1 plus Q2 over 2. Because again, these are going to basically cancel this. These are going to add to 2R and cancel the R on the top. So you're going to be left with 1/2. And you get half the charge. It makes sense. If they have the same size, the spheres, your new charge is going to be half of the total. Yeah. Yeah, you're going to give the one sphere half of the total. Okay. So maybe call this equation 3. You're trying to find what Q1 is. All right. Q1 prime, I guess. So you can do now these two, I guess. Q1 prime is R1 over R2 times Q2 prime, which is this stuff. And you can see that the only change is that the R1 trades for the R2 rather trades itself for R1. That's the only change made. And now we've got the charge on both of these conductors. We can find it now. You see? Done and done. That's how the charge reshuffles. What other questions did I ask here? Draw a diagram, find the charge and respective charge density on each sphere. So if you want the charge density now, obviously, the last thing to do, I want to finish exactly at 9. That's why I'm rushing. So I don't keep Kelly around, you know. So over here, if you want to find the charge density on these spheres now, sigma 2 prime, obviously is just the charge that you have on it divided by its surface area. And sigma 1 over here prime is obviously this, the charge it has now on it divided by its surface area. There you go. That is all there is to it. So if you're given a problem like this, just know the two things that you need to keep in mind is charge conservation. The sum of the charges after you connect them should be the sum of the charges in the beginning, okay? Whatever the charges were in the beginning, you have to maintain them. Even if you had negatives over here on one sphere and positives on the other and you got annihilation, when you sum the charges in the beginning and you sum them after the connection, they should yield the same value. So keep that in mind. However, the potentials will shuffle around. In the beginning, they were the values that you see here, but in the end, when you've connected the spheres and the charges have shuffled, those Qs are different, right? Those Qs are different. And the process, the transfer of charges happens when the potentials equilibrate. That's when the stop happens. That's when they stop moving. So that's the problem I wanted you to see. Okay, hopefully I filled you in enough. Any questions?
Could we have a quick overview of given I'm trying to figure out how to explain this.
Okay, Grace has to go. You can go, Grace, don't worry. I'll post the recording and you can see the rest of the way. If we do like 5 or 10 minutes more, okay? And Kelly, the same for you. But Olivia, what were you saying?
Are you able to go over like general steps for solving like finding E field versus like Gauss's law questions, voltage, like whatever algorithmic approach there might be?
Okay, so my recommendation, okay, if you are presented with a symmetric situation, such as the ones we saw today, okay, you see Gauss symmetry. That's why I've broken, you see how I've broken here the E field chapter, Gauss symmetry, non-Gauss, and they're both talking about electric field. That's the two categories. The Gauss symmetry, honestly, Olivia, there's a handful of like problems that you can apply Gauss's law on. Lines, planes, okay, and they have to be infinite. So infinite line, infinite plane, infinite cylinder, I guess infinite coaxial cylinder. Again, this is considered a cylinder to me. Infinite slab, and a finite sphere. That's it. You can't do Gauss's law on anything else. You can't do it on, let's say, a finite plane, a finite wire, a finite cylinder. No, you can't do it there. That's it. One more place you can do it, I guess, is a parallel plate capacitor. A parallel plate capacitor, when you apply Gauss's law, is two infinite planes resting like this. I consider that a plane again situation.
Wait, sorry, can you repeat what we can apply on Gauss's surface again?
Again, the only ones that you have to deal with ever in this course, infinite lines, infinite planes, infinite cylinders, finite spheres, infinite slabs, and parallel plate capacitors. That's it. You're never going to see anything else. So if you see on your exam, and it's a very long cylinder, Gauss's law. If you see a concentric shell system, Gauss's law. If you see a ring, not Gauss's law. If you see a finite line, not Gauss's law. If you see a hemisphere, not Gauss's law. If you see a cone, sometimes they've thrown a cone on questions, not Gauss's law. If you see, what else can I come up with? A triangle of charges, a square of charges, a rhombus of charges, some kind of configuration of point charges, not Gauss's law. Those you'd have to do with, adding vectors together from each electric field. Do you see a pattern? There's only like 7 or 8 scenarios that I can outnumber from the top of my head that use Gauss's law. And you can vary those scenarios. For example, the sphere, you can take it and do weird things with it, right? You can break it and have it have charge densities like this, conductors, surrounding insulators. But the point is, this is a spherical charge distribution. Spherical charge distribution. You can see it here, spherical charge distribution. All the charges are on spheres. So it has Gaussian symmetry. And
Wait,
even
what's like Gauss's symmetry is like?
Gauss's symmetry is the arguments that I've been making over here. Remember, Gaussian symmetry basically means that not only do I know the electric field direction right now, I have the ability to introduce a surface that obeys the rules for using Gauss's law. That's what it means having Gaussian symmetry. You are able to use a Gaussian surface that moves the electric field outside the integral, like we've seen so far. That means having Gaussian symmetry. Okay? Other people define it differently, but I define it like that. Gaussian symmetry means you can introduce a surface that moves the field outside the integral. If there exists such surface, you have Gaussian symmetry.
Okay, so like if an example of a line charge, it won't have a Gauss's symmetry, right?
It does, because I can introduce the cylinder here, and with that introduction of that surface, I can pull the electric field here outside the integral. If I use the sphere as a Gaussian surface here, that would be wrong. I couldn't take the field outside the integral.
Oh, okay.
Since Gauss's law only talks about like 3D enclosed shapes,
Yes.
is Q enclosed always going to be the integral of like the charge distribution times dV?
Depends on the dimension. I've told you that. You got to look at the dimension of the charge density. In this case, it's a 1D density. So what happens is, if we want to find the charge enclosed, we got to multiply lambda by the length that we've enclosed here, right? It's a 1D charge density. That's why you see me do that.
Okay, so
And-
just in general, it's always going to be like the dimensions charge density times
Yes.
the, like whatever that unit of area
Yes,
would be.
here is always the integral of your respective charge density and the respective length associated with it. So if it's 1D, it's the integral of lambda dl. If it's 2D, it's the integral of sigma dA. If it's 3D, it's the integral of rho dV. In this case, it's the integral of lambda dl. We just did not do the integral though here at all because, well, lambda is constant, right? It would be pulled outside and then you'd have just the integral of dl, which in this case is just L. So we didn't do it at all. But I'm telling you, you should make it a practice that you write it like that. The integral of the respective density with the element that you're integrating.
I also have a question, like, does Gauss's law like apply, doesn't matter on like if it is a uniform charge or a non-uniform charge?
Okay, good question, Kelly. I will say it really depends on the dependency of that density. So let me explain. If right now you were pumping these charges as you went to the left, let's say, you were pumping these charges. You see here, if I was pumping these charges, if I had a linear charge density that increased as I go to the left, that's what I'm trying to imitate here. Well, what would happen is these electric field vectors would grow as we go to the left. And what do we notice? This part of the cylinder no longer has the same electric field strength as this part of the cylinder. So we can't pull the field outside. We can't do that because the E field is space dependent now. You see?
Um,
But watch the cool thing, because you asked a very good, solid question. Okay. So usually in lines, it looks like you're screwed if you have a dependency. You can't use Gauss's law. But what about over here? Where we had, where did it go? The cylinder. There we go. This one. It said the cylinder has a dependency. Why does this work then? Right? Why does this work? You know why it works? Because right now, let me see if I can show that on this diagram. So right now, we have, if we are at a constant R, you see here, if our cylinder for the Gaussian surface sits at a constant R, everybody that's sitting right here right now at the same distance from the z-axis, so I'm going to point a vector to show you what I mean. Everybody that's sitting right now here, okay, I'm going to move the vector to show you. Everybody that's sitting here right now, okay, has the same charge density right now, because that side that I'm showing you right now, that I'm pointing with that arrow, it's sitting at the same distance from the z-axis right now, okay? And according to the formula for our charge density, it only depends on R. So all the points right now that are sitting on that side of the cylinder, and conversely, on the other side over here, right? All these points are sitting at the same value of R, guaranteeing that the charge density on the surface of the cylinder right now is uniform. For example, I think Kelly's seeing it now. So in the case of this Gaussian surface, if this R was 5 meters, the charge density all around the blue cylinder would be 5 times rho naught. You see what I'm saying?
But what if if I have there's a question on our quiz, it's like there's 2 dumbbells that is connected with it's like 2 connected, and then one of the balls that is like charged and one of it doesn't have the charge. So does it mean I cannot use that? I cannot use
Gauss's law there, I'll tell you that, okay? But it reminds me of the problem we just did with the 2 spheres. You're not supposed to find the electric field of such a situation, by the way. It's not possible, okay? With like the 2 spheres in the vicinity of each other, you can't do it.
Okay. So like both of them has to be like having charge.
Can you explain what you mean, Kelly?
Do you mind if I share my screen? Maybe.
No, you can
No?
share your screen. Okay, you should be able to share. All right, so you're saying here, choose the following case for which the electric field at any point outside the object can be calculated easily from Gauss's law. No, not B. What's the third one there? What's going on the third one? I'm a little curious. So is the third one the only one that has charge right now is the right guy? Okay, so it's a dumbbell. Okay, so you guys see again the example here that she has? Look carefully. The second one, absolutely not. Okay? You can't use Gauss's law. The first one, absolutely yes. Okay, we literally. But look at the third one. What do you think? I'm just curious. If I ask randomly here, Bogdan, let's ask randomly. What do you think, Bogdan, about the third one? Look where the charge is.
Yeah, because the charge is only in one of the spheres, I think you can use it because there's no charge in the other
Uh-huh. We only care about the charge distribution when we're judging Gaussian symmetry. So right here, assuming again, be careful here, Kelly, assuming again that these are insulators. If they were it's impossible if they're conductors right now in the third one, because if they're touching, the charge would spill, right? So they have to be insulators in number 3. But what we can tell from this, okay, we only focus on the sphere that has the charge. And we go, wait a minute, that's a sphere of charge. That is equivalent to scenario 1. I don't care what's touching right now, that sphere, as long as it's an insulator, it's a conductor, this kind of messes things up. But I don't care right now that it's being touched by another insulator, right? I care that the charge is spherical in nature right now. Right?
So like for the second picture, it is not like a sphere or any shape that satisfies.
Exactly. You can't. The electric field from the second one's like all sorts of weird shapes. You can't enclose it with any particular shape to satisfy Gaussian symmetry. But the third one, you literally only need to enclose the right sphere with a sphere to do Gauss's law. That's what I'm trying to say. It's the equivalent of the first one.
Oh, okay.
We're only paying attention where the charge is. Again, only if these are insulators in the third picture, like the guys interacting, because if they're conductors, again, you understand, right? Like we're gonna have flow of charge, it's gonna become the second picture if they're touching.
And also I have this question as well. Wait.
You have more?
One more. This one, like, is it because Gauss's law doesn't care if the charge distribution is constant or not?
So applying symmetry and canceling out DE's X, Y, and or Z components only works if and only if the charge distribution is constant for any symmetrical shape. If it's constant. No, not really. Wait, no. Let me show a counterexample to tell you why not. You did a counterexample. Was the charge density here constant?
No.
No. Did you have symmetry and you canceled components?
Yeah.
So what do you say to that?
So it doesn't have to be a constant.
It's false.
Okay.
It doesn't have to be a constant. You see it here varying from the example. This is a counterexample that immediately tells you it's false, what they're claiming.
Oh, okay.
Okay. Now, for you, Olivia, I just want to say that, again, for Gauss's law problems, how you approach them, a typical Gauss's law problem like here, any Gauss's law problem, you always come in, okay? You can, instead of me writing the steps, you can view the video, I guess, and make a transcript of what I'm saying right now in steps. But your first job is to determine the direction of the electric field. You cannot walk in this problem. So if you're suspecting that you have Gaussian symmetry, make sure you do determine how the electric field will go. And it can be as fundamental as looking at the charges and seeing how the electric fields will go and deducing that, for example, this guy will have an R-directed electric field. You need that. You can't do anything if you don't know that. Then you go, okay, what kind of dependency am I expecting? That's number 2. What kind of dependency am I expecting? Who's going to tell me that? Well, some of the time you have to do a mental kind of, you have to do like a mental picture of, does it matter if I'm between these two positions that differ in X? Do I see something different underneath me, or is it all the same? If it's all the same, then these experience the same electric field. Do I see a difference between these two positions that vary in Y? Obviously right now, no. So I suspect that distance from the wire here will have an effect on electric field. And that's how I get that. So first get the direction, deduce it, and then deduce the dependency. Okay? Both are important. Once you're here, now you're asking, what kind of Gaussian surface should I use? That's number 3 now. So you look at the electric field. The direction here is in the cylindrical R. The dependencies are, who can help me? A cylinder can help you because the field lines that go in the R direction, the normals of the cylinder on the side are parallel to that. So that satisfies that. And then, because the dependency is only on R, the surrounding, like the wrapping of the cylinder, its surface, right, the side of it, has a constant R, which ensures the electric field is going to be the same across the surface, which is criterion 2. So once you fill these 2 criteria, you got your shape and you use it. Now, while you're using the shape to do Gauss's law, you got to break down, that's like step number 4. You got to break down, okay, the regions based on the charge density. So if you have a charge density that switches, you have it for R less than A and for R more than A, you know that you're going to have 2 distinct electric fields. Similarly, if it splits into 3, the charge density, you're going to have 3 electric fields, and you got to investigate each region independently. Now, for step number 5, while you're in the integral, okay, try again to never forget how to do this stuff. The left-hand side only cares about the Gaussian surface, never about the charge density. But the right-hand side cares about the charge density. So what this means is when you're trying to find, let's say, what to put on the right-hand side here, you're looking at how much charge is enclosed. So you can see here that all I care about is this lambda times the length that I've enclosed by my cylinder. I don't care about this gap here, right? The gap above and the gap below. I don't care about that. It doesn't contain any charge. The charge is all squeezed on this one-dimensional line right here. That's what it is. So if I have the lambda of this line, and I know the length of my cylinder, I multiply them together to get the charge enclosed. Versus on the left, I'm working with a cylinder right now, right? You're saying, how big is the surface area of that cylinder on the side? 2 pi RL. So don't mix the 2 sides.
So, wait, do you mean 2 sides as in like the sides that are like the round faces versus the curved faces? Or do you mean like sides of the equation?
I mean the 2 sides of the equation.
Oh, okay, yeah.
So the left always looks at the Gaussian surface, but the right focuses on what the Gaussian surface contains. Sometimes the whole surface is filled with charge, like in the case, for example, of your cylinder. Here, the full volume of the Gaussian surface was filled with charge, right? But when we were out here, do you see that I had a space here that did not include charge? You see, on the right-hand side, I need to put only this volume right here. So don't by accident put this volume on the right-hand side. So sometimes the volumes agree, like in this problem, in this case over here, what you put on the left-hand side is the surface area of this cylinder, and what you put on the right-hand side is the volume of the cylinder. Yeah. But in this case, on the left, you put the surface area of this cylinder, but on the right, you put the surface area of this part of the blue cylinder. You see, because there's no charge here. So don't mix that up. And that's it. You just solve. Try to avoid integration if you can. The only time you will have to integrate, I swear, that's a tip number 6. The only time you will need to integrate is when the charge density is not uniform. If it's uniform, you don't have to integrate this. The left-hand side, you never have to integrate. If you're doing Gauss's law for the electric field, you never have to integrate the left-hand side. It will always be the area of your Gaussian surface, the part that's getting electric field. Never have to integrate this side. I've never integrated it in front of you, never. But the right-hand side only gets to be integrated when this rho is nasty, when it's not constant. So like here. Put my money where my mouth is. Again, we did a problem later. You can see it here again. Did I integrate left here? No. Did I integrate right here? No again, because rho was constant. I pulled it out of the integral, and this was just the volume between the two concentric spheres. Okay, so avoid integration. The only time you need to integrate is going to be on the right-hand side, and only when this is non-uniform.
Okay. Sorry, could you repeat that one more time? I think I zoned out a bit.
Yeah. So again, when you're doing Gauss's law, the left-hand side, if you pick the correct surface, of course, doesn't need integration ever. Like you can find what this area is. It's just asking for the area of the Gaussian surface. But the right-hand side skips integration only when rho is constant. If it's like in this case, right? But if rho is not constant, you have to integrate. You have to integrate like here. When we put the rho in, obviously we have to integrate it. Okay?
That makes sense. Because, if it's not uniform.
Yeah.
I have a question. So when do you use rho or when do you use sigma? For Gauss's law, do you always use sigma? Or rho?
You look at the charge density. Okay, this is 3D that we're working on. It has a volume charge density.
Oh, okay.
So
can I look at the object if it is 3D or 2D?
yes, yeah. We said this here. If it's 1D, lambda dl. If it's 2D, sigma dA. If it's 3D, rho dV.
Okay, I got it now. Thank you.
Okay. So on the non-Gauss stuff now, okay? How to find the electric field there. You're always looking for symmetry, right? Like most of these problems that they're going to throw at you, they have symmetry, and you got to work out, yourself what that symmetry is. So I would say if you have a non-Gauss problem, first step is to see if there's any symmetry. So you determine that you determine that if the problem has a mirror, like if this side mirrors this side, you're going to have symmetry. You see how here, this side is a mirror to that side, you have symmetry. Okay. So you're looking again to see if there's a mirror, if the charge distribution, I should say, is odd or even. If it's odd or even, you will have symmetry. In this case, it's odd. You have odd symmetry, okay? If it was a cosine, you have even symmetry. Okay. And if it was a constant, if we just had this piece, it would still be an even symmetry because the right-hand side would be the same as the left-hand side. But in every of these three cases, you literally approach it the same way, right? You pick like two antipodal, we call them antipodal points here. They're literally the opposites. They're like mirrors. Like imagine this is a mirror. This guy's looking at himself at the mirror. That's his reflection, right? That's how we pick those points. And we do the symmetry argument. So that's step number one, finding if there's symmetry or not. Step number two, you always want to remember the definition of the electric field element. And then you go and fill it in.
What do
Step
you mean by electric field element?
This, I'm highlighting it.
Oh, the KDQ over like length squared.
Yeah, because if you break down right now your charge density into little points, these points are like point charges. That's why they have this electric field format. It's not coincidence that this looks exactly like your point charge formula, because these are points essentially in space and time. They're points. So their electric field formula is like this. So you gotta remember this walking in. That's step number two. You put it down. If you have symmetry, then find what component remains. If not, you'll have to solve the whole thing here. You guys, 90% of the time, you have symmetry, okay? So you find what that symmetry is. That's, again, the step 1 and 2 are together, I should say. Like putting this down and finding the symmetry are happening at the same time. If you have symmetry, well, then find out what survives. Here it's the DEY. Okay, how is it related to DE? You see how we found it here? So I guess that's step number 3. If you have symmetry, how is the remaining component related to the DE, the original? Okay, step number 4, what's DQ? So that's where Kelly will be thinking, you know, am I dealing with lambda, sigma, or rho? So what's DQ here? Well, you're dealing with 2D, that's going to be a sigma. So DQ is going to be sigma dA. That's what we see here. Step number 5, what's dA? Well, what coordinates are you in? You're in polars. You know how to find the dA in polars. It's like r dr d phi. So put it down. That's step number 5.
Oh, that reminds me. We have to have like dA, dV, etc. memorized for each coordinate system.
I would if I were you, just to be safe, but you can derive them on the spot if you're clever or if you're visual. Okay.
Yeah. Okay. I was wondering, like, do you have like a flow chart of?
Yeah, I'll give you the note.
Oh, okay, cool.
Okay. So that's step number 5. Step number 6. Okay. This sigma, state it. That's step number 6 right now. State what the sigma is. Because, yeah, it's given here. But what if they told you right now that you deposited charge Q on this, right? And it's uniformly distributed. You'd have to calculate sigma, right? In terms of that Q. You'd have to calculate it. I lost Kelly right now. I don't know why. I think she just dropped. But yeah, you'd have to calculate. How would you calculate it here? You take the total charge that you have on this, the Q, and divide it by the surface area, which is half of pi r squared here. That's the sigma. So that's step number 6. State the density. State it. If it's like given, then beautifully. Go on, do your thing. But if it's not, you have to calculate it. Okay? So what's next? Step number 7. Now is the difficult step. You've got all these things down. You gotta turn them into coordinate variables. So if you have a variable in here that's not in the coordinate system, you gotta find how it's related to the coordinate system. That's all we did every single time. You're lucky here. Okay, you're lucky here. All of these, you can see this is coordinate variable. This is a coordinate variable, right? Coordinate variable. You're all good. No translation needed. But let me show a counterexample. this guy, okay? Look at this. You go, where was it? Let me see. This guy, okay? You go, yeah, sine theta is d over curly r. So curly r is d sine theta. But theta is not a coordinate variable, right? I'm in Cartesians. I can't accept that, right? So I gotta find out what sine theta is in terms of some x or y. What is it? Well, I can go and see over here. So sine of theta is d over curly r, and curly r is the guy right now that will make the connection. Using Pythagoras, I get what curly r is in terms of a running variable. So essentially, Olivia, here what's happened is I've turned this sine theta around by doing this. Do you see now that I have sine theta written in terms of a running variable in Cartesians, the x? I had to think, though, to do the conversion. I had to do a little bit of investigation, right? Why did I want the sine theta, by the way, in Cartesians? Because it's involved in the symmetry here. You see it? I got to kill this guy in favor of something that has x, y, or both. That's the difficult part, the number 7. That's the difficult part, okay? So by the time that you get to the integral, you're still on number 7 right now. By the time that you get to the integral, you want to walk in here, okay? You will not see anything but running variables of your coordinate system. You know you've done it right when I don't see any other variable here. These are constants. These are constants. That's a constant. But the variables are all coordinate variables. You know you've done it correct when that happens. And then you solve the integral. That's step number 8. Solve the integral. The steps that I'm telling you, same across all the problems.
Oh, okay. Yeah, like what I'm trying to do is, worst comes to worst, if I forget how to like handle specific situations, I just want to be able to at least have the process down. Because that's like a better chance for part marks.
Yeah. So by all means, that's why I'll give you the video, put it down the steps, and if you forget, run through them.
Okay, yeah.
Them are the same. All of them, Olivia, any electric field you're deriving. Again, we said step number 1, check if there's symmetry. Look, again, symmetry. There it is in the DEZ. So I'm writing it down. Step number 2, put down the DE element. Don't forget what it looks like. Step number 3, what is DQ? This is hemispherical shell. So the charge is on the surface. So I'm dealing with a 2D shape. So it's a sigma. So DQ is going to be a sigma times dA. I put it down. Step number 4, we said, what is this dA in the coordinate system that I'm working in? Well, I'm in sphericals. This dA is, in this case, capital R squared sine theta d phi d theta, not dr. Okay, we're not integrating along dr. We're on the surface. So that's what our dA is, and I wrote it down here. Sometimes you see me do things in a different order. That's okay. I'm just following the recipe that I gave you right now. So step number 5 was, if I'm not messing them up, was the state v density, right? Here's a case again where the density wasn't given. You were given the charge. How do you find sigma? Take that charge divided by the surface area of your hemisphere, q over 2 pi r squared in this case. There it is. That was step number 5, I guess. Number 6, okay? Number 6, yeah, I might have messed them up a little bit. Number 6 and 5, I might have forgotten something. But number 6, start converting all the variables into the coordinate variables. Everybody's going back to these. So if you find yourself having this guy, think, what is this guy in terms of these guys? In this problem, they're the same thing. Okay, they just happen to be the same thing in this problem. Like this R is this curly R. We can see, like, you start from the middle of YX coordinate system here. This variable is going to be your R. I've done something here to show you the projection of the components. However, we are considering this to be the origin when we're doing this problem, like right there. This is to be the XY plane for this to make sense, what I'm showing you, right? So you can see again, this guy is secretly the spherical R. We understand that. Okay, so we identify, and not only that, not only is he the spherical R, but he's a constant because we're always on the surface. He is capital R. Anyways, so that's good. We eliminated that. This is a running variable, right? What else? That's a running variable, right? That polar angle is a running variable. So I have no problems right now. I can put them all together now, like in here, and form my integral. I have no problem now. And then integrate this. So I'm on step number 7 there, where I'm basically putting the integral together, and step number 8, I'm solving it. Same steps every single time. Okay, and as a rule of thumb, I guess, for the voltage, okay, how do you deal with the voltage now? So the voltage steps, okay, if you want to do voltage, that integral, number 1, put it down. Okay, this integral. You're looking to find the voltage at some point. That's your reference. Okay, so your integral is going to go from your reference to that point. But this integral might need to be split into multiple parts, depending on how many, again, electric fields you traverse. So step number 1 is to write it. Step number 2 is to see if this needs to be broken into more than one integrals. Remember that, because going from P naught to P might involve a switch of electric fields. So plan your trip out, see what electric fields you traverse, break this integral into the appropriate number of integrals, okay? Straightforward
Okay,
stuff.
so like for this problem specifically, could you zoom out so I could also see the diagram?
Yes.
Okay, so in this case, the reference point we chose is one along the boundary.
It's right here.
Oh yeah, sorry.
And this
So-
is the point of interest right now.
Oh, okay, so like they'll tell us find it at this point and then we pick P naught.
Yeah, or they will just tell you find the potential function, in which case, again, you need to know right now to be abstract, like I said, set a P naught and then find the potential at P with respect to that. That's what's happening here. So not to confuse you, Olivia, we're now in step 3. So you've put down this, step 1. Step 2, you've broken it down into its pieces, right? However many integrals you need to do on this side. Could be 1, could be 10. Okay, step number 3, the important one, the difficult one. Do I need to take a reference away from infinity? When does that happen? I've told you earlier in the term. If you have infinite distributions, 9 times out of 10, you cannot use infinity as your reference. Why? Because your potential function is going to break.
Wait, for which case, sorry?
Infinite charge distribution. So if it's an infinite line,
Oh, like
plane.
an infinite line, infinite plane. Okay.
Yeah, there are exceptions, like the coaxial cylinder. You can use infinity for that one, but there's a reason. Okay, but 9 times out of 10, you cannot.
So say it is like an infinite plane. What would you recommend then? Just some arbitrary point on the surface, or?
Yeah, we put a reference point. Again, we solved this, and I showed you here. There it is. I was like, again, take a reference point somewhere away from the plane, and that's your point of interest up there, right?
Okay.
So
and you just integrate from
Yeah.
that location.
from P
Okay,
naught
it
to
doesn't
P.
actually change like anything aside from the bounds, as I can tell.
Nope.
Oh, okay, that's not too bad. Because the one thing I find with this course is like I'm able to solve things slash like it's intuitive if I'm kind of guided through it. To actually produce all of this from scratch,
It's difficult.
I'm not quite at that point.
Yeah.
Yeah.
So that's why I'm giving you a strategy, right? Again, for the third step, you judge it. If it's, again, an infinite distribution, please, Olivia, use a reference point at a finite distance, like I do here. If it's an infinite distribution, use a finite reference point. It's the opposite. So if you see an infinite thing, use a finite point for your reference. And you're going to check at the end of your work if you can use infinity. Sometimes you can, like I said, in the coaxial cylinder. So check at the end when you have the potential function. If you plug in for your reference's position infinity, do you get infinity or do you get a finite number? So if the answer is you get infinity, nope, can't use infinity. Sad. So can I use here infinity? No, because that's going to break this. That's going to diverge to infinity again. No. Sad, but true. So all you can do is leave it like this, and you can make v of z naught equal to 0. That's the only simplification here. And I told you why with the relative height example. You can make the v of z naught 0, and that's it. Now, what if you have a finite distribution right now? What if you have a finite one? Here-
Finite infinite should be fine, right?
Yes, for finite, infinity is always fine.
Okay.
Always fine. Okay. So we don't need to discuss that one. So it's the infinite ones that cause problems. So when you see infinite ones, just drop a reference point at, somewhere, do the potential with respect to that, and then check if you can put that point, sneak it to infinity. If not, that's okay.
So for the like when we're just picking an arbitrary reference point for P naught when we're looking at like an infinite charged plane or like an infinite surface,
Yes.
is there literally any difference for where you put it? Like, is there some choices that are no, it's just
But in the case of the plane here, do you see what I'm doing with these points? I didn't put P naught underneath the plane here because there's a different electric field acting there. I want to keep them in general as a rule of thumb and the same, on the same region. Now, it doesn't matter per se if you put this underneath, really, real talk. It's going to confuse you, okay? And when you're doing the integral, what is going on? Because you measure z upwards right now. If you put P naught here, it's going to mess with you. It's going to be like,
it just screams
so that's like
some
negative.
numbers.
Yeah, that's like negative z naught. What am I supposed to put in there right now? So I put them in simple locations where the variable is really simple to understand what to do with. It doesn't matter if it's here, I'm telling you, but it will confuse you when you're thinking of negative signs and stuff. So, now I was at step 3 there with that potential. Step 4, okay. I have one more for step 3. What if I don't have the electric field? You just assume that I have the electric field available. What if I don't have the electric field? Right?
So do we have to find it then?
Usually, yeah. But what if it's hard to find the electric field? Well, in that case, let me remind you. So you see over here, non-Gaussian symmetry. So the third case of your third step is a situation like this, where it's way easier to use the potential of a point charge and integrate it to find the potential of the entire distribution at your point of interest. So you have 3 situations at step 3 that could happen. Number uno is a case where finding the electric field right now is more cumbersome than just doing this. You're going to be able to tell when you should use this. Every non-gauze situation, everything that is not a plane, an infinite plane, an infinite line, an infinite cylinder, everything that's like that, this is the way to go. Every non-gauze situation, if they ask you for the potential, go this route. I guaranteed, go this route. If you want to make a note as you watch the video later, again, as a methodology, if you cannot use Gauss's law on the charge distribution that you have at hand, this, 100%. You can see how quickly we get the potential from this, right? The approach to solve this, follow the steps in the electric field. There's no symmetries for voltage though, because it's not a vector. But everything else is the same. Find the dq. This is a 1D thing. You know, that means lambda dl is going to give you dq. Find what dl is. All the steps that we did for the electric field, the non-Gauss electric field, apply here besides the symmetry. Okay.
Okay, and DQ is, I'm just trying to remember because there's a lot of things in this course that feel very similar.
Lambda dl, sigma dA, or rho dV.
What was it, sorry?
Lambda dl, sigma dA, or rho dV.
Oh, so it just represents like a small surface that we already have charge distributed and we're going to integrate. Okay.
So, non-Gauss situations, this guy. Gauss situations, you can usually they'll ask you anyways to find the electric field first. Okay, so you'll do Gauss's law, you get the field, and then you're split. You're split between the two options. Am I having an infinite distribution or a finite distribution? George said if it's infinite, I got to put a reference point at a finite distance. If the charge distribution is finite, George said I can use infinity as my reference. So you go those paths and you do the integral method.
Okay.
So for non-Gauss, this. Okay, that's a non-Gauss situation. Equivalently, that's another non-Gauss situation. Same deal. You use the
Okay,
dV
so in
element.
this, yeah, like in this situation, what I would do is first I notice that it's it's not Gaussian. So in this case, I would just have to go with the integral of dV, right?
The dV element, yeah, the dV equals
Yeah.
kq over r. Yeah, you'd try to integrate that, exactly.
Oh, okay,
Yes.
yeah, cool. So in this case, dq would be, I don't know, I guess like the radius.
Hold on, why don't I test you here a little bit, and why don't I test you, okay?
Sure.
Okay, you tell me what, like, I don't want the full solution. You just tell me like the path that you would follow. Like, what would you do overall? Like, no, I don't want the steps. Like, what branch are you following in? That's all I want. So what if you had a solid conductor sphere right now? Solid conductor sphere. And I want you again to think potential. Okay? How to get the potential everywhere.
So first instinct is that because it's equipotential, it's constant. So I don't think I'll need to be doing any integration.
You have three choices, remember? The dV element, the E from Gauss's law, okay? And then you have P reference here at, a finite place. And then the same thing, right, over here, but the P reference is at infinity.
Oh, okay.
Which branch is
Well,
this?
in this case,
I don't know.
I would say 2.
You'd say 2.
Although wouldn't one be easy as well?
Well, we do those exercises in Phys 242. You don't want to, okay? They're painful.
Oh, okay.
You can do it with 1 too, yes. One is like, this is the big boy, okay? He covers everybody, but he's also difficult for a lot of problems, right? So that's why we have escapes to these two. This guy's the big boy that covers everybody.
Mhm.
You can do this for any distribution, right? Unrestricted, but he's difficult a lot of the times. This here is difficult to deal with in general.
Okay.
So,
So
the K,
let's say I selected option 2 then. So I want to
You'll have to
approach
tell me
it
more.
using
That's-
E field with Gauss law.
yeah, you find the E
Oh no,
field
I just
with
want to make
Gauss'
sure I have an
law.
understanding and then I know the process.
Yeah.
Like as opposed to just short-term memory, I want to make sure I'm like able to like mentally walk myself through a full solution.
Yeah, yeah.
So I see the shape. Here I recognize, okay, Gaussian symmetry, not infinite, so I can do an infinite reference point.
Yes.
So then I do the integral from,
Sorry, we picked the second option that said finite. I just noticed that.
oh, okay, yeah, I read it as,
I'm being a little bit not careful here. It's the infinite
Oh, it's all
option. You
good.
said it though. You said it.
so I take that infinite point, I go from the infinite point to, I guess, whatever point is given. And then in order to do that, what I have to know is the E field, and I have to know like dV, right?
You have to know the E field and you do the integral. So let me write them nice over here, and you'll pick based on the distribution that I show you. So dV is K dq over curly R, okay? And dq here we said what it can be, right? Depending on the dimension and all that, right? So it depends what you have, and then you would basically solve the voltage as the integral of dV. That's method 1. Method 2 is use Gauss's law, okay? So use Gauss's law over here to get the electric field first. Okay, that would get you the electric field. Then you would use this, okay, this integral, but the reference point would be at infinity. Okay, this P ref right now would be at infinity. So again, I'm going to say this is infinity. Okay.
Okay, and like instead of DL, it would just be like D appropriate surface here.
Of course, you're going to pick it depending again on where you're doing the walk, right?
Mhm.
And the third one, the only difference is this is finite. This is like R naught. Some R naught away. Okay.
Okay.
So these
and-
are your 3 options.
Okay.
I have
And
more questions, Olivia. Hold on. I want to test you. I want to grind you 1 sec, okay?
oh, okay, yeah.
Trust me, I have good ideas to test you. So again, I want you to think about this sphere problem. And I'm going to give you right now, again, the fact that this is, let's say, a solid insulator right now. So it has a row. I just want you to tell me, answer my questions here. How many electric fields are you going to get from this situation right now? This has a solid, it's a solid sphere, charge density row. How many electric field regions are you going to get?
So there's an E field inside, but not outside to my knowledge. So just 1, and it would be like on the inside.
There's an E field outside. You surround this with Gaussian sphere. You have charge enclosed. There's an E field outside.
Oh, okay. Which is am I thinking of? What am I thinking of then?
Here. So rho, I'll just show you. I gave you a hint, you guys, before about how to approach this. I was telling you, look at the charge density, how many times it splits.
Oh, okay. Yeah, well, because you'd have to do like its own calculation for each.
How many electric
So
fields
what
would
I
this
did here,
yield?
it should be 2, I think. So from what I understand, the top one, do I take like big R to be the radius of the insulator or the radius of the Gaussian surface?
Insulator right now.
Oh, okay. So in this case, the first one you could do like Q enclosed. And then the second one, would you do Q enclosed, except you'd have to do it with the Gaussian sphere instead of the conductor we have?
I'd always put your Gaussian sphere mentally on the picture and assess the regions. You have to place it right now at some point for R greater than R and at some point R less than R. So it's up to you where to position it. Okay. But my question was like the question that I really wanted you to understand is how do I know what to expect? See here, the charge density is something inside the sphere and nothing outside. That's two regions. And that's where I need to investigate the electric field. It will switch because it depends on the charge density, right? The field.
Mhm.
So we'll switch when the charge density switches. And that's why I expect two fields here. Yeah?
Right, because
Okay.
like each piecewise kind of defines the different charge distribution, and the different charge distribution results in different like E fields.
Yes. And now for the potential, okay, this was a discussion for the E field. For the potential, which branch do you fall within here?
So when there are two, I tend to get confused. What I am going to say is for little r is less than big R.
You know what? I'll make
My
it even
instinct-
I'll make it even more in depth. So E field, here's like what to do for the E field right now. We're not going to solve, we're just talking about it. So the expectation is this, and you're doing Gauss's law right now for both of these, okay?
Yep.
Okay,
Okay, so it does work for both then.
okay. So you're getting the electric field here from Gauss's law. So obviously not option number one. What about these then?
Well, since it's not infinite, we can take the infinite reference point.
So it's
So
number
V2.
two. Yeah. Okay, let's try this again, okay? Let's try this again. I'll keep a copy of Gauss's law here, but let's try it again. Now I'm gonna tell you, you have, let's see if you're gonna be able to determine this. I hope Bogdan, are you still here, Bogdan? Because I haven't asked you a lot, I'm just talking with Olivia.
Yeah, I'm still here. I'm listening.
Okay. So let's say, Olivia, you have this situation right now, and this is again concentric insulators, okay? Here are the radii. Okay, and each of them has a different charge density. So how many electric fields do I expect now?
So we have three different densities, which means three different fields.
Are you sure it's just three?
Oh, well, there's are they all,
Just
okay,
look how I'm writing them
so-
down and you'll see what I meant there. Is it just
Yeah.
three?
Oh, yeah, like for when it's outside of the entire system, that's also a remaining one.
So how many electric fields do you expect?
So that would be four then.
And you got to investigate all of these regions, right? To give the electric fields everywhere, right? Every single one of them. You see? And you'd apply Gauss's law right now on every single one of them to find the electric field everywhere. So suppose you did that, you got the electric fields now everywhere. Where do you
How
fall?
does Gauss's law work for like R is greater than C?
You have the sphere sitting outside.
Oh, okay.
So you close all of this charge. You'd have to find how much charge this totals to, how much charge this totals to, how much charge this totals to, and add them all together.
How would I go about like finding how much charge is in each section?
Easy. You take over here the total then to be row 1 dV, row 2 dV, etc. Right? And this dV here, again, if let's say again, Olivia, let's say again that these are constants, okay? These are constant densities. We're not going to give them a dependency. So basically, row 1, and it's dV here, well, I want that volume, so it's going to be 4 pi a cubed over 3. Then I do the next one. Row 2 times its volume, well, that's this area over here. So to find its
Right,
volume,
4 pi over 3 times b cubed, and then the last one would be the same thing, but with c cubed.
not b cubed, careful, minus a
Oh, yeah.
cubed. Yeah.
Oh, b cubed minus. Oh, yeah, because you're taking like that
Mhm.
way you're not doubling the like you're not
Not
factoring
counting
in
this. Yes.
Yeah.
And
Okay, that
similarly,
makes sense.
the third one you'd get with its own dv here, which would be this space over here, which you can try if you want.
So it would be first off 4 pi over 3, and then would it be c cubed minus b cubed minus a cubed, or is it
No,
included
just
in the...
minus b cubed. So
Okay.
the b cubed would take care of this
Oh
area
yeah,
over
because
here.
that covers that radius.
Right, and that answers how you get that charge closed. That is long, but it's what it is.
Okay, so then that's Q total, and then you just that over epsilon naught.
That's the right-hand
okay.
side.
Cool.
Okay, so now that we're done that, okay, you understand we split it into 4 regions. You get each one with Gauss's law, but what branch are you falling over here?
It's going to be 2 because it's not infinite.
Exactly. You're getting it. So let me test you again over here.
Okay.
Continue on. The next one I want to try with you. Okay. What if I had right now, let's say, a disk, and I'm trying to find the potential right now. I'm trying to find the potential along the axis here. There's a disk of radius r. And I want to find the potential right here at point P. So what now?
So we're finding potential?
Yes. So immediately you need to ask yourself, can I use Gauss's law on this?
Nope. Not in
No.
the closed surface, right?
So immediately, what's your answer for the 3 options?
The first path, dv.
First one.
Okay, and then what we would basically do is, this is 2D, if I'm not mistaken, right?
Yes, it's a disk. So dq,
Okay,
sigma dA,
cool.
right?
And then the denominator, what was it again?
Curly r.
Yeah. I'm
That
just trying to
is-
figure out what that would...
That connects the little piece that you're going to use for dq to the point of interest. That's curly r.
Oh, okay, so it's just the distance from the dq to the point that we're of interest.
And that r is going to move around here as you integrate.
Okay, and in this case, the reference point would just be at dq? Like
We
at
don't
that
need
spot
here.
up
When we're
top,
doing
or-
this,
Oh, right, we don't need it.
it's already absolute.
Right, because
When
we
we're
don't
trying
have
to
to worry about like bounds for that.
No, yeah, we don't.
Okay.
All right, so you get the difference, right? And again, if we have a cylinder over here, right, that's infinite again. If we have a cylinder that's infinite, and I give you the fact that it's, you know, it might be again coaxial like this. So I could have like, I don't know, honestly, like the possibilities are endless here. We can make this to be a solid conductor right now, and we can make this to be an insulator. The possibilities are endless, or the other way around, right? We can make this to be an insulator, and we can make the surrounding be a conductor right now. So in any case, I'll give you this just for the sake of it. But again, how do I get potential? That's what we always are looking out for. So look at this. Does it have cylindrical symmetry, Gaussian symmetry? You know, what's going on with it?
So this one would be, from my understanding, this would be Gaussian, and the Gaussian shape we use is cylindrical. It's an
Okay.
infinite surface.
how many electric fields do we expect here? So be careful about this. Rho right now, let's say that this is radius A, and this is radius B. What's rho doing? Well, it's being rho, well, inside the first one, and it's being 0, as you can see, between A and B, but it's also being 0, you know, outside, as you can see as well. So, you know, how many electric fields do we expect here to see?
Well, since they're both the same magnitude, there would just be 2.
I got to analyze this guy, and we believe that after A, the electric field is going to look exactly the same. Even though we're traversing that conductor surface here, we believe that it's going to look exactly the same, and it will. It will, Olivia, because when you're enclosing right now with your Gaussian cylinder, this piece, this amounts to some Q over here right now. It amounts to some Q. I don't want to make it per pink because you'll confuse it with the induced charges, but you know, this bit here that I'm highlighting, this bit of that cylinder amounts to some Q, right? That's what I'm trying to say. It amounts to some Q. And again, on the outskirts, like when we're moving out here, because this is a conductor, what it's done is it's aligned itself like this all over, right? And when we make the cylinder go out like this, when we're investigating the outside, I want you to see that overall, these being enclosed right now, they cancel. So you're left still with the original that was enclosed in the insulator, right? And that's why we have these two cases giving you the same electric field. When you're on the very outside, these induced charges that are being enclosed, they cancel completely. As we've said before, these don't matter. I've been screaming this tonight. They don't matter to Gauss's law.
Okay, and the way that I interpret the diagram is like, so we have Q, positive Q. So when we're looking at like that inner pink cylinder,
Yes.
that would bring the negatives toward Q, but that would leave the positives on the edge of that inner pink cylinder. Which
Pink
is
cylinders are the Gaussian surfaces right now, right? For the R between A and B, and the bigger cylinders for R greater than B, right? So I'm doing these, I'm doing these regions here right now with those pink cylinders. And I just wanted you to see that the inner one contains the same enclosed charge as the outer one.
Okay.
In this case.
I'm not fully sure I understand why the enclosed charge is the same.
Okay. I don't know if I've given you the wrong interpretation here. These are supposed to be the same length, I guess. Not that the length will matter in this result, but visually I want you to see it a bit better. So the only thing I've done here is just stretch this cylinder out. That's all I've done. Okay? I've just stretched it. And it's now enclosing these two. Okay? The outer one has been just stretched in the R direction to include these. And these are canceling each other when they are included together. They're on the surface. As soon as you cross the surface, these don't mean anything.
Okay.
So
yeah,
both
I think
outer,
the part that's confusing the most is like the outermost condition.
Yeah. Outer against cylinder, the outer parts here, they always cancel on both sides. Right? And you're always left with that real charge on the insulator.
And I just want to make sure that I'm understanding why the charges are like getting induced the way that they are so that they cancel. My understanding is that positive Q is in the middle, so it attracts the negative ones for the innermost Gaussian cylinder.
Everything, okay, Olivia, let me interrupt you.
Mhm.
Everything outside your Gaussian surface right now is not interacting with you. Never. Okay. You don't see, if you are the inner pink cylinder, you do not interact with the induced charges on the surface of the blue cylinder. Everything above you is irrelevant when you're doing Gauss's law. So all that you're
how do
seeing
the
is what's
induced
under.
charges work for the blue cylinder then?
So the blue cylinder is reacting to the presence of charge here. Your Gaussian surface is an imaginary thing. It doesn't exist.
Okay.
And again, the Gaussian surface only cares about what's inside it. That's by law, by the actual Gauss's law. Only cares about what is inside it right now, not what is outside it, what is enclosed. The right side says enclosed. That's not enclosed. You are not interacting with this at this stage.
Okay.
You're interacting with it here, and the interaction mutually annihilates.
Okay. Yeah, I'm still not fully grasping how ignoring the Gaussian surfaces, how the induced charges are working for the blue cylinder.
So the blue cylinder, again, if right now in here, you're enclosing positive Q, in this piece of the cylinder, you better have gathered up over here, like in this piece that I'm saying, highlighting here, you better have gathered up minus Q and left behind positive Q holes. Okay?
So
Because
I'm curious why the way I'm interpreting the diagram is, so we have the the charge in the middle, and we have the blue cylinder around it. So
Yes.
the way that I would interpret it is that because Q is positive, the negative charges in the blue cylinder would attract to Q, and that would
Well,
leave positives.
yes. Careful. You don't want to mix the machinery of Gauss's law with the real, how the charges interact in reality here. You don't want to mix what an imaginary surface is doing, okay, with like the real actual situation that the charges are obeying. Okay, so the real situation that the charges are obeying doesn't matter, doesn't have to do anything with Gauss's law. Okay, the real situation here is you have an electric field that's coming in from this cylinder, okay, like this. That's what's happening in reality. You have an electric field and it needs to be stopped because you can't traverse the conductor surface. We've said why, okay? So if you need to be stopped here, you gather negatives to absorb those field lines on the very inside surface right now to kill those E field lines. And those leave positive holes that migrate to the outer surface like this, right? And of course, those positive holes continue the electric field outside. That's the picture of what the charges are doing, right? In reality. That's what's happening in reality.
That makes sense. Yeah, okay. I think the part that was confusing me was that I didn't understand why the negatives weren't getting pulled in, but that makes sense because the positive repels and then the negative takes in. So the negatives wouldn't have to move. So
Right,
you
they
have to put them
can't
on the
come
edge
in
so they
here.
don't break through.
They can't.
Yeah,
There's,
'cause
again,
it
a
goes
potential
against what
barrier.
they're- Yeah.
They're on the surface, stuck on the surface. They can only move on this. So there's a potential barrier right now. They can't jump the air potential barrier and come in here.
Oh, right. They can't go inside.
No,
That's right.
it's not a solid space.
Okay, that makes sense then. That
So
makes
they're
sense why it's
sitting
stuck to the surface.
as close as they can to the positive, but again, they're bound on the surface.
Mhm.
Okay.
Okay,
Now,
that makes sense.
the Gauss's law that I was telling you about, okay, when you put the inner cylinder again, and put the inner cylinder like this, what you're enclosing right now is just a chunk of the real charge here. You don't care that these are here and these are here. They're outside you, so they don't matter. Okay? And they're uniformly, that's the point. They're uniformly outside you. If they were lumped together, like somehow we had a charge density here that was like non-uniform like this, then that would matter. It doesn't matter because we have uniform, again, we're sitting in the middle and we're being, tugged on one side by that negative and tugged on the other side by the equivalent negative. So the overall tugging is zero. But if we had something non-symmetric like this, you can see how this messes things up.
Yeah.
Okay, so
that helps a lot with clarifying
good.
Like charge distributions for these kinds of problems.
Good. Okay, So that's what's happening here, and that's why I enclosed right now just this guy for the first cylinder. Then if I did the second one, I just, made it to go a little bit further outside, like this, right? The only change here is, yeah, you're including these now, but they cancel out, right? So that's why we're claiming the field here and the field here are the same, because the same charge is being enclosed between the two regions. These enclose the same charge, no matter how you make the Gaussian surface.
Okay. Yeah, and it also has to do because of the way that the E fields work. Like we don't have to worry about any sort of vertical change because of how
It's uniformly
like, because of
distributed,
how
the
it's-
charge, yeah.
Yeah.
We don't have to worry about the vertical aspect. Now, on the very inside, obviously, like if you make a cylinder this big, right? What I'm enclosing
Then that
in it,
would
right there. You make a cylinder this big right now, I'm only enclosing this amount of charge that is very different than what I was doing before.
yeah. Because as
That's where-
opposed basically from what I understand based on this, so we have the pink Gaussian surface inside and it doesn't enclose all of it. So
Yeah,
it would
only
be
a fraction.
different than before.
Yeah.
Yeah, like if we were to put one that has the same height but just encloses the actual entirety, it wouldn't be the same Q enclosed.
Yeah, exactly.
Okay, that makes sense.
So now you know there's two E fields and we can get them from Gauss's law. This is an infinite cylinder. Which scenario do we fall for the potential under?
Infinite cylinder means we can't use an infinite reference point. DV would be annoying, but these are Gaussian surfaces, so we don't have to worry about it. So it would be the third option. The
Third option.
like the finite reference point. Just pick a random one and then integrate.
There you go. Okay, that's the deal.
Okay. Cool.
All right. So I'm trying to think of another one here. Maybe I'll think of this. Okay. Well, you know the answer to this, but what I'm going to do is, again, I need another wash and break. So I'm just going to give you
That's all
these to think about. Okay. So here's like your infinite plane right now. Okay. With charge density sigma. Okay. Infinite plane. I want you to think about the electric field. Okay. And I'll take a minute and I'll be right back. Okay.
Okay.
All right.
So I think I have my answers.
For it.
So for E field, there would only be one because we only have one charge distribution. For potential, we would not use the infinite option because we have an infinite plane. So I settled on using option 3 because we can turn it into a cylinder, and in that way we have the Gaussian surface.
Yeah. Exactly.
Okay. Yeah.
Exactly. So you do up option 3. If you didn't have the field available, you'd use Gauss's laws with a Gaussian, like either like the pillbox, it's a little cylinder, or like a rectangular prism, or sorry, a rectangle, basically.
Okay. And I just want to make sure, so because this plane is infinite in both directions, what would dA look like for this?
Here in this case?
Yeah.
Well, if you're in Cartesians right now when you're doing this, right? So dy and dx.
Oh, okay. Okay. So then how would we, so dA is dy by dx. Yeah, could I just see the integral for going to get Q enclosed?
That's what I was going to show you. So again, you do this, you decide here how big the pillbox is that you're going to use, right? Like we're not supposed to do these integrals anyways, but let's say you use like this big of a pillbox right now. Okay, I'm not going to draw it perfectly, but you get the point. Okay, so that's like the pillbox that we're using for the Gaussian surface, like that. And you can see right now, the area enclosed is a projection of like the top surface on that plane. Like it's like I'm shining a flashlight in this direction and projects the shadow of the top surface to the plane. So if you wanted to set up and ask how much charge is enclosed right now, and you made the Gaussian pillbox, let's say, in this direction, you made it X, and in this direction, you made it just Y. You're taking this double integral right now, as you can see, from 0 to X and 0 to Y. So you get, obviously, that this is just going to be sigma XY. That's how much charge you're
Okay, that
enclosing.
makes sense.
So
I'm
obviously-
just looking at the second line, and I just want to make
Obviously,
sure I'm
Olivia, here-
understanding it.
Like you see that if we go and do the entire plane, this is infinity and this is infinity, so we get infinite charge, right?
Mhm.
Okay. Yeah, so that's how you would find if you wanted the charge enclosed. But we don't even do that. Like we just immediately on the right-hand side, we pull the sigma outside right now, okay? So instead of doing the integral, we're doing instead sigma dA. And then I always ask you, what is the area right now of this yellow patch? And you always said XY.
Okay, yeah. Yep,
I
that
told you,
makes
whenever-
sense.
Whenever you can skip integrals, skip them.
Okay, that makes sense. Plus, like the general, the way that I interpret this is if I'm taking the integral of like a rectangular area, it is always going to be like, sorry, the integral of like a small portion will just be like X by Y, because that's, I'm not explaining this
Yeah.
very well, but I
You can
think
call
this should
these
be good.
variables whatever you want, okay? You can call them L and H, you can call them D and whatever. I just call them X and Y
Yeah.
to trigger your attention that the Gaussian surface, you can decide how big you want it to be. I want you to understand that X and Y are variables that you decide how big you want to be, and it doesn't change the answer.
Okay, so we literally just say X and Y.
Yeah.
Pretty much. That makes sense.
There you go.
Okay.
And you said the third
Is there
option here?
anything-
Yeah.
Yeah, like a finite reference point, just something random.
Exactly. I think you're good.
So is there, okay, is there anything else that's extremely important that I should know? Because like I mentioned, I'm very good when it's presented and asked, but when it's like starting and coming up with it, maybe like,
Not
is there
really,
like
Olivia. I
a-
think my opinion is that you should be very good at what I taught you here. If in case again you ever forget how to do again volume integrals, but I think Math 119 also help you there. How to do volume integrals by filling up your shape with little cylinders, sorry, solid cylinders, and then the area integrals are like rubber bands around your shape.
Yeah.
Okay, so these
Okay.
again techniques here, please remember them. They're from math, okay? Filling in with cylinders, solid cylinders, and filling in with rubber bands and stretching them. Another thing I want you to just have in your mind is that the discussion I had with Kelly about building blocks. So your building block, again, think of it as something that you will smear to fill the thing that you want to fill. So here again, the building block is a rubber band because I'm going to smear it throughout the surface of the cone and fill it. And that way I'm going to find the surface area. If I was doing something else, let's say, is that the only case I had here? I guess.
I'm just gonna quickly check what's provided to us, because what I'm thinking of doing is like that little thing about,
I'll give you this.
okay, how many,
I'll
like,
give you this.
yeah, because like the thing that really helped me just there was like splitting up, okay, E field, how many, and then voltage, which approach. I was thinking of writing that down like immediately on the scrap piece of paper, because that's like
Yeah, and
very,
you
very
have like
good for starting off.
some kind of
Yeah.
plan, like a flow chart. Yes. And it's
Exactly,
again,
yeah. That's what I'm aiming to do, is make like some sort of flow chart, or at least like something that I can treat as a prompt that can self-direct me in the right direction.
Of course. And here, let me pause the recording one sec. So just look. Don't just answer my questions. Look at this. Charges distribute over the surface of the thin hemispherical shell. Gauss's law or not Gauss's law?
Oh wait, hemispherical is half a circle, right? So no.
No. So if you want to find, it says here, calculate the electric field, okay? So you find it from the non-Gauss approach that I was talking to you earlier, the dE equals K dQ over R squared. You solve that, okay?
Okay.
You've been
One thing I
given,
always mix up is like KdQ over R versus KdQ over R squared.
take a look
I
at the
always kind of mix
units.
that up.
Units per coulomb is the units of electric field, right? I guess it's hard to see the units right now when K is involved. I can't advise you there because K has weird units, but yeah, always take a look at the
I'll
units.
just treat it as something unitless, just to simplify it in my head. So then,
Look at
okay, so
this.
the field, okay.
Sphere, this is the charge
Um,
density. You see that it's R dependent, so that means we still
Mhm.
preserve that, you know, the R symmetry on the sphere, right? We preserve it. So can we use Gauss's law?
Should be able to.
Yeah, of course. So how many regions?
Yeah,
do we
because whatever
see?
you. So it should just be. If we're going, okay. I would say just one.
Are you sure?
Oh, I didn't even see that. That would be two.
So I mean, again, even if they didn't tell you this, the sphere finishes somewhere and then it's zero outside it. Even if they didn't tell you this, I just
Okay.
want you to catch it, that you're gonna need to look inside it and outside it right now, and that's it.
Okay.
Does that make
yeah.
sense?
Mhm.
Okay, so which one? Which one are you gonna use for the potential right now? Which method?
So we have a Gaussian sphere. It's not infinite. So I would say the method that uses an infinite reference point.
Exactly. I'm just forgetting where I was here when we were doing the side quest here. I forgot where I was writing. My God. Okay, that's okay. You know what I'm asking, so it's good. All right, look at this shell, hemispherical shell. Can you use Gauss's law again?
No, because it's not like a closed surface and it's not symmetrical.
Okay, so you have the charge density. Be careful again with this. Okay. The center of the shell is at the origin, the coordinates, whatever, in the XY plane. What is the electrostatic potential of the center? You can't use Gauss's law. So automatically that gets rid of two options. Which option remains for the potential?
That would be the dV.
Solve dV equals kdq over r.
So what I would do in this case, when it says at the center, my reference point would be what, like 0? Or
So the
my
center of the shell is at the origin of the coordinates and the base of the hemisphere is in the XY plane. So like the XY
oh
plane is
right, we don't
here
need a rep. Okay.
and the hemisphere opens like this.
Okay.
Like look at my
I think
hand,
one
it
thing that
opens
I
like
just momentarily.
yeah.
Okay. One thing that I forgot is that we don't need a reference point if we're just doing the integral for dV.
Exactly. You don't need it. Right. Okay. Look how easy they become once you have that in your mind, right? I mean, there's a lot of sphere stuff over here, but I want to do a cylinder one. Hold on. There has to
Okay.
be something. They're all spheres. What the hell? They're all spheres. Come on now. Oh, there we go. All right. All right. All right. Charge is non-uniformly distributed. Uh-oh. Uh-oh. On a sheet, a very large sheet of thickness D. The sheet is very large in the XY. The cross-section of the sheet is shown in the figure. The volume charge density. Wait, it's not a sheet. If it has a volume charge density, it's a slab. Why can't they just, be careful with their words? So anyways, it's a slab, okay? It's a slab where R naught is positive. So they show you here, right? Okay, we want to calculate the electric field. Answer the questions below. Can you use Gauss's law to calculate the E field at P1 without using superposition? Explain briefly. If your answer is yes, draw it and do it, right? Else skip. and answer C. Okay, so it's a cosine function for x between 0 and d. For x between 0 and d, our charge density here basically drops like this. It drops, it goes down. Well, that happens from both directions. That happens from the top direction here. That happens from the bottom direction here. Charge density goes down to 0 as we head toward D. I mean, that's what I observe here, unless I'm crazy. So for x equals to D, we have cos of pi over 2, which is 0. Yeah. So the charge density, you can think of it going like down to 0 over here, and then down to 0 from the below part. So actually, what I could do here is claim that I do have Gaussian symmetry, okay? I just have to be careful. Is the electric field the same? If I use a Gaussian surface here, underneath me, if I use a cube as my Gaussian surface here, underneath me right now, I have varying charge density. So the strengths of the electric fields that are hitting my bottom surface, they're variable. So I would say no, you can't use Gauss's law, but you can use clever symmetry over here to find the field wherever you need it. For example, again, what I can do here, Olivia, is pick again a point here, a dV over here, pick a dV over here. Well, I'll have to put, again, we're not on the x-axis though. I'll have to think about that. But this is an unlikely problem to make it on your exam because it's actually difficult to solve. So I don't know if I should pass or not, but I have to think about how to solve at P1. I would solve at P1. I don't know, this cosine. Yeah, I don't think you can use Gauss's law again, like because like this face over here of the cube you would fit here, it would receive different amounts of electric field throughout its space here. Or would it? It would underneath it. Wait a minute. No. Okay, I got it. See, it takes a minute even for me to click sometimes. So what's happening with your slab right now, you can think about it, your slab being again here. It's really weird, but listen to this. Here's like your x-axis, okay? And again, we don't have a y or z dependency, I remind you that. So let's say the z dependency is like here, the z-axis, and let's say the y-axis is this way. That's your slab right now, okay? That's your slab. And the charge density, like I said, if I was to plot it on this, what's happening is, as a function of x, it's getting dumped. The charge density is going like, down to 0, right? But here's the catch, Olivia, okay? If I put right now a Gaussian surface that looks like this, okay? Look at this one sec. This is incredible. So if I put a Gaussian surface that looks like this, just a little pillbox, that's what we'll work on this. Anyways, do you notice right now that this thing has extent? Look at this. This thing has extent in the y and in the z, but not in the x. You know what this means? What this guy here right now receives a constant charge density. Whatever its position is right now, whatever its position is on the x, this side, whatever it is, d, who cares? Whatever it is on the x, it's receiving a constant charge density. I think the charge density was rho naught cos pi x, in this case d over, hold on, let's not call it d then, yikes. Let's call this like something else, like s. So it's receiving this constant density right now, that side, pi s over 2d. And that means along that surface that we do get the same electric field coming in. But this electric field is dying out as we go toward the surface. It's really strong, as we go like this. This is how it will look like. It's dying out as we go toward the surface because the charge density, well, actually, we have to do the integral of Gauss's law to determine this properly, but we know, guaranteed right now, we know we're going to have the electric field have an X dependency because the charge density has an X dependency. We know that, guaranteed. So I don't know exactly if this is going to grow or shrink as we go toward the boundary in the X, but I know that it's not going to be the same strength, and the strength will depend on where you are along the X. I know that 100%. So because this face of my pillbox is sitting at a constant X, it's receiving the same electric field throughout it. And I can use Gauss's law with this pillbox like that. It will have some electric field going through here, 100%. Isn't that interesting? So you can use Gauss's law. I put my Gaussian surface like this. If I were you, because the electric field is a function of X, I'd do the clever thing and put the Gaussian surface here, because the backside right now wouldn't receive any electric field since it's sitting at 0. E of 0 would be 0 here because it's dependent on X. That's what I expect, at least, and I would only be receiving electric field at the front here. So I'd have to only use, in my Gaussian integral, this little thing on the left-hand side, that pi r squared disk. That's it. What I enclose would be this. I'd have to do the volume, whatever this volume is, times the charge density of the slab. And since the charge density is varying, you'd actually, to find the Q enclosed, you'd have to integrate. Because the charge density is varying. Remember, it's X dependent. And that's the difference. This is a difficult problem, though. Okay? But I hope I brought a little bit of light on how to do it and if Gauss's law is applicable. It is, because the pillbox will have a side here that has a constant X if we set it this way. And that means everybody here will get the same electric field because the charge density is the same at that point. It's really interesting. And really good stuff, really interesting stuff. So I wanted to show you if you have like a cylinder type of question, but I guess you don't. You have a thin disk immediately. Can you use Gauss's law?
Thin, no, because it's a disk.
No. So it has.
So you would have
you-
to. Okay,
Depending
so
on-
to do potentially, you'd have to do integral of dv.
Yeah, that's what they ask,
Okay.
potential right now. So do dv. Can we use Gauss's law? No. Okay. I mean, explain your reasoning. I don't have an enclosed shape that can obey the two rules, that I can have the normals be parallel to the electric field and have the electric field strength be uniform across it. I don't have a shape like that to enclose the disk.
Right. Okay. So the difference between A and B, why is it harder to do the potential at a point on the circumference versus at the center? Is it like there's maybe trig involved with getting to the?
So what do you mean by that? Like why we put the DQ upstairs, like on the disk?
Oh, I mean, like, so looking at question A versus question B. Question B is worth more marks, which I'm assuming usually means that it's a harder question. So what makes it more difficult being on the circumference versus the center? Like, what other things need to be taken into consideration?
So if you put it at the circumference, if you have the charge disk like this, let's say, and you want to do the integral, obviously we know this is very easy at this point, but if you want it to do right now on the circumference, now this becomes like this, and it's a thin disk here, Olivia. So the problem here is that it could possibly diverge if we have charge on the outskirts here and we're on the charge. You're going to realize that the electric field will diverge. Okay, it will blow up. That's the problem here. But the dV may not blow up, depends. So if I'm doing the circumference, if I put a point on the circumference and I want to find the dV there, it's the geometry that makes this more difficult, because now, look at this, I have to there is symmetry here too. I don't care though about it because I'm doing dv and I'm not doing vectors. So if I pick a small dq right now to connect me up there, I want you to see that this is a much more complicated integral now all of a sudden, because this is curly r, right? And curly r, you need to find it in terms of like coordinate variables, r and phi. And that's the job that's difficult here. So you need to start thinking, how could I possibly find what this is, right? There's ways, of course, you can do it, okay? Start introducing things, right? You start introducing simplifications. First of all, why put P here if I can rotate the coordinate system? It just says on the circumference. So what am I doing here? Why not put P at a very nice point like this, right? And then wonder what this is. Now you're picking something up. Look at this, that's R. That's capital R. You see, just by rotating the reference, you see here what's going on? So that's 2R. Uh-huh, okay. And that is gonna be something, of course, that's gonna be curly R. Okay, and then we are wondering, what can we do here, right? To solve for what curly R is. I wanna find it as a distance right now, right? I wanna find it as a distance. So I did this in general. You can start by doing a simpler point. Maybe you can see the pattern if you did, for example, like a point here, a DQ that's over here. Maybe we can see a pattern here. I'd move my DQ around to see if I can nail what right now R is going to be. And this is going to be complicated to do. That's why it's worth more marks. So, you know, you can start trying your best here to figure out what this is going to look like. You know, you can ask, for example, what's the position of DQ right now in terms of like R and phi? You know, you would have a vector pointing to it like this. I'd have to employ here the full physics 242 machinery. This looks pretty bad, but that would be like R naught in physics 242 or RQ, depending how you want to label it. You have the R here, and you have another vector that points to point P right now. So I'd have to employ the full machinery of physics 242 to do that for you. Okay, that would be like RP, the vector. And you can see that, okay, you can see that basically R, curly R, is equal to the difference between these two vectors, right? Let me explain. Take that here, and I wish I could just reverse it, but if you reverse it, you see the resultant here being literally curly R. That's what's going on. So you have to take RP and subtract the vector RQ, and then you have to find what these vectors are right now. So RP seems to be literally R x hat, and RQ needs to is right now has components, unfortunately. So it has here two components. You can use the phi angle to define them. It has two components, one going upstairs like this, and one going, of course, this way. So I'd write it as here. I'd write it as R, because this is the radius again of the disk. R. Are we doing a ring or a disk again? I forgot.
It is a, I think that's a ring.
It's a disk.
I keep mixing up what they like visually mean.
Okay, can I just show you the ring? Because the disk is even more complicated than this. I just want to show you the ring, how like you would deal with this if you were in physics 242, because that's a 242 problem, and I swear to it.
Great.
So if you have this RQ right now, you can see that it has two components, one in the X, one in the Y. You can get them by using, again, trig here very quickly. So this here is X, right? I would use the fact that RQ, the size of it is capital R. So I'd be like, okay, that is capital R, cos phi, x hat, okay? And then plus R sine phi, y hat. And what do you know? Look what I get here. R 1 minus cos phi x hat plus R sine phi y hat. And that's your curly R vector. And if you want to find the size of it, which is what you want to put, you know, on the denominator of dE, you see what you will do, right? The size will end up being here, R square root 1 minus cos phi squared plus sine squared of phi, like that. And I think you could open it up, I guess, here. You know, you could open this up if you wanted to, right? Because you'll get a little bit of a simplification, if you can see here, right? Because that's just one. So you'd get here for your R's size, you'd get 2 minus 2 cos phi, or root 2R 1 minus cos phi. Wow, right? And that's your R, your curly R. Your DQ is still the same stuff that it was before, lambda DL to solve this. And your DL right now, literally just R d phi. And your lambda would be Q over the circumference of the ring. And you got it all right now to put it in your dV. So dV would be K dq over curly R. Okay. And then you start putting things in. So dq altogether would be lambda, which is q over 2 pi r, times the L, which is r d phi. And then your denominator is r, which you found to be root 2, capital R, 1 minus cos phi. There you have it. And so V is the integral of K, Q. I guess here we have 2 root 2 passing outside. We got the R's combining, so R squared. And we have a pi. Okay, wait. These cancel actually. Okay, so we go 2 root 2, get the pi there, all good. And then you're integrating d phi and this function here that is funky from 0 to 2 pi because we're doing the entire ring. And that's it. Don't ask how I know these things, okay? Let's just say I really like electromagnetism.
Wow. Okay, yeah,
But-
that is, I'm hoping they don't give anything like that on the midterm. I will say, I know the 119 midterm today seemed intentionally easy. I don't know if that's just a 119 thing or if it's like, oh, we're in person now, so we're gonna be fair.
I don't know,
I'm hoping
Olivia,
that
this
they're
is not-
gonna,
This is not first year stuff. Come on now. Okay, like this is bullshit in my opinion. You shouldn't be doing
yeah,
this.
like I was I was talking to a friend of mine at Western and he was saying, yeah, you know, we don't do double integrals until year 2. And I'm like, I was doing triple integrals with functions that have dependent variables in the bounds on day 1 of this term. It is insane.
It is, and I'm not a fan, but I just want to show you, like I have Salma here for Phys 242 this term. And well, I guess this is a good example, right? Like just showing you here, this, not this. See, they do Gauss's law here. Electrostatic potential for a hollow sphere with finite thickness. Just what we did right now. And there's the dependency. Okay. Home assignment 5 is 242.
Wow.
So again,
And
here's
like
your-
they're
here's your
getting
thing.
given like a lot of time to work on it too. Wow.
Coaxial cylinders.
As far as I can tell, yeah, like as far as I can tell, this will be the end for physics after 106, I think.
Hopefully.
In terms of like the courses I take for my degree, but I'm not entirely sure.
Hopefully, Olivia, because you see, again, I don't know why they're hammering you so hard. But that's why, you know what, in all truth, I guess I will put this in the recording just for fun, but this is, again, I guess, what keeps what keeps me busy, right? You guys weren't being,
Mhm.
unfairly treated. I wouldn't have students, so I guess it's a good thing for me, right?
Right.
So
Yeah,
keep,
well,
keep
thank
getting
you.
busted. Tell Brenda to keep making it harder, okay?
Yeah. I am going to, yeah, midterms tomorrow. I'm gonna probably head out. This has been very helpful. Thank you. Like, specifically what I appreciate is kind of being able to create those prompts and like, once there's like a flow chart / you can kind of classify the problem, it becomes a lot easier.
Yes.
So I think that's something I'm gonna try and put a lot of focus on instead of just trying to do it without having structure.
Yes. So before you go though, Olivia, here's what I'm going to do. I'm going to stop the recording here. Do you want to squeeze any questions in? You good?
I think I'm good for now.
Okay.
If I can think, like, if I'm gonna do some practice problems tomorrow morning. If I run into anything that really stumps me, what
Let me know.
time are you? Okay, yeah. What time are you going to be active on Discord? Because I know my midterm is from 1 o'clock to 3 something, and that
So
might be too early.
I'll tell you. Okay, I'll stop the recording here. I'll tell you this stuff and we'll talk about this. Okay. So let me just end it here for the session.